I'm MC Toon, and it's Tuesday night. We've got another debate. This is the second debate of the night. Debate discussion. Not sure exactly how to declare this one, but this is Joe Hill or EftupWorld. Welcome, Joe. How are you?
I'm good. How are you doing?
I'm great.
Am I loud and clear?
Yes, I hear you fine. And live chat. Make sure. Yes, let me know if it's too loud or not enough, or maybe they just want me to mute you the whole time. It might be. I'm not.
You know what? I think if you read the chat, I think that's probably what you'd find.
So this weekend, it's kind of funny. I went camping this last weekend. It was MEA weekend in Minnesota, which means there's no school on Thursday, Friday for pretty much every school district, except for private schools. We homeschool, but we still do that because our kids do stuff with other kids. So we were camping just right near Mille Lacs, which is one of the biggest lakes in Minnesota. And for some reason, I thought you lived in the town right south of Mille Lacs. Onamia. Yeah.
Oh, okay. No,
I don't know why I thought that, but I'm like, that's not where he lives. And so
I'm
anyway,
60 miles south of there. So.
I know. So I'm driving up there. I'm like, this is a long drive for Joe, because you work down in the cities here.
I work south of you a lot of the time. Like I work, south of Afton, like by Prescott a lot of the time. So.
Yeah. Anyway, I'm like, anyway, so that was a little, and I took a picture of the Onamia water tower, still thinking that was the town he lived in. I'm like 10 feet from his house. And I'm like, wait a second, that's not.
Then he goes, oh wait, you don't live up there, do you?
So anyway, welcome, Joe. You mentioned, I think in a Facebook comment, that there was something something you wanted to talk about in particular, about star elevation, the angular elevation of stars, or the sun, one or the other.
Well, it was something I noticed about the sun.
Okay.
I think it's obvious that throughout the day, we can all see it going about 15 degrees per hour, moving in the sky.
Yes. And
when it gets, I don't know precisely, like I haven't taken some precise measurements, but when I put my drone up in the air, it gives me sort of a platform where I know how long it's been up there. You know what I mean? So if I do a time lapse, I know the length of the time lapse. And what I've noticed is, actually, if you look at this video behind me, I'll try to zoom in a little bit. I just have it playing repeated. When it gets down, I don't know how many degrees, like 10, probably under 10 degrees or something like that, it doesn't go down anymore. And this is not always. This is not always, because obviously we've seen, I actually just uploaded a video of the sunset looking over Mille Lacs, and the sun is going right down. It looks like it's sinking into the ground. So I'm not saying that this is the only way the sun sets, but it doesn't appear to, it certainly doesn't move at that 15 degrees per hour when it gets down close to the horizon. And I think that if we're going to measure, and I think you'll agree with me on this, if we're going to try to measure anything from the ground below, I don't know, 15 degrees or so, we're looking through the thickest, most dense part of the atmosphere all the time. So it's always going to look different depending on what the conditions of the air are. You know what I mean? And they're always kind of unpredictable, but so part of the sun not moving that 15 degrees per hour is just getting caught in that dense, looking through that dense atmosphere.
Yeah, and we have a pretty good understanding of what's going on there.
Yeah, no, right? I would agree. I would agree.
And I think did you watch, or were you in the live chat of the video I did last week where I covered a lot of the basics,
the geometry for flirps?
Yeah, geometry for flirps. Where
I watched it. Yep.
I think I spent more time talking about refraction than geometry in that video.
Yeah, and that's actually, geometry is one of the subjects that I hope we can, and actually I'm hoping that you can help me tonight. Like, okay. This is because I want to do some math, like actual, just run some numbers when it comes to like the angle of the sun, and if I don't want to like misquote you or something, but if I remember what you were saying is that on a flat surface, a sun being up in the sky, no matter where it was really, would not be able to set. It would always be visible. Is that what you've said? Kind of?
Yeah. And we can
Okay.
we can go over the math for that.
Yeah, I want to. So
All right. So let me, because we talked about the refraction and the rate of the sun moving vertically as it nears the horizon. So if people recall what I talked about last week, and just the normal condition where the index of refraction is higher near the ground,
yeah.
and going closer to 1.0 is like the definition of no refraction, 1.0.
Okay.
So if you can see more things than you would see without refraction, what's happening is you're actually getting more stuff that's visible, but it has to take up the same amount of space, same amount of angular size. So if you take,
I think I know what you're talking about.
Yeah, if you take 2 degrees worth of stuff, 1 degree, the bottom degree is below the horizon, and the other degree, if there was no refraction, you would just take up that bottom, and you pack it into 1 degree, everything has to scrunch
like
down.
this, right? Sort of like that, right?
Yes.
Yeah, a little bit.
It's a good look for you.
Yeah, I got more.
So yeah,
I was thinking about this one though myself.
oh, nice.
So this is what a globe head would actually look like.
It looks like your hat is painted on.
Look what my hat actually says. You'd be surprised.
Romans 3:14 flat earth. Oh, is that from Nathan Roberts?
Yeah, it's from Nathan. Yeah, it's from Nathan Roberts.
Does he even exist anymore, or did he
I don't
just
know.
stop?
I hope so. I hope he's all right.
Did he stop existing because we don't see him?
Well, like my only thought about Nathan Roberts, and this we're not talking about this, I know, but my only thought about it is that he started saying some weird stuff about people, like nice, very nice people in the flat earth community, saying that they were something, and I think like that really
he basically went, everybody's a shill but him.
I was one of them. I mean,
really?
I was. Oh yeah, he didn't like me. He did for a little while.
Oh, he liked me a lot. I debated him, and he's my number one fan. No.
He's your buddy. Yeah.
He did not like that. Yeah, you still have that effect on, just so you know.
Oh, it's not an effect.
Oh, it's okay.
This is what I had the effect on earlier. No, I'm just kidding. This is just normal me right here. I can make my head go. Okay. All right. Back to our talk here.
All right. All right. Silk. It looks like Silk Spectre was accidentally timed out. Yeah. So sorry about that. Okay. So, all right. We went over the compression. So you want to talk about the actual math of it, right?
Well, can I just mention kind of something I'm thinking about the geometry of it, and you can tell me what you think. Maybe it doesn't make any sense what I'm saying, but I'll try to put it into words.
Okay.
You know how people, the idea of the sun setting and the bottom of the clouds, like the clouds right above you, they can get lit up by the sun, and
yeah,
that would seem to be impossible on a flat surface because the sun is above the clouds, right?
Yes. Yeah.
And that would be, with the geometry that we would do, that would make sense that the light from the sun cannot get down underneath the clouds if it's way high.
Yeah, and it would have to curve back up somehow.
Yeah. So here's my question about that. And I'm being genuine here. I'm not like trying to flirt around with you. If you are standing at the ocean or wherever, it doesn't really matter, and you're looking out at the sunset and it's going down to the horizon, and now I'm not talking about a flat or a curve or anything like that. I'm just saying it wouldn't even have to be the sun necessarily, but any light that's down almost touching the horizon. When I stand there and I look at that light and I look at the clouds right there, would it not be normal to think that the light from the sun could come, because the sun setting or whatever it is, like going down or going away or whatever. But wouldn't that light just be able to go right up to them clouds and bounce back to me, reflect back to my eyes? And I know the geometry doesn't make sense. So that's something that I'm like, I really don't think we can necessarily portray reality with geometry.
So we could I think maybe we could have two hypotheses here.
Okay.
Right. So hypothesis one of them would be that the Earth is flat. The other would be that the Earth is a sphere. Right. So you hypothesize the Earth is flat and the sun is a certain elevation above it, higher than the clouds. Your prediction would be then that the bottom side of clouds could not be directly illuminated unless somehow there is extremely strong refraction causing it to curve very much up, or a very good reflection, like a super good mirror.
Like a mirror, yeah.
Yeah.
Actually, I was going to bring that up.
Because a lake on a very calm day could potentially act like a mirror, but trees and grass and dirt and buildings don't. So like when you see a real good example is the in Washington, the mountain in Washington state, where you see the shadow of the mountain on the cloud.
Yeah, I think that's because the mountain sticks up above the clouds there.
Well, the mountain actually is below the clouds, and you can see a little gap between the top. Sometimes the clouds come farther down, but it doesn't matter either way. The shadow of the mountain is up
on the clouds.
And so that means that the light, the direct path of light, has to be coming somehow up. So the hypothesis would be for a flat Earth that it would not be possible without either strong refraction a reflective surface, but there isn't a reflective surface.
Bendy light rays
to the west. Yeah, so bendy light is the only thing, but we don't have, there's no plausible mechanism for that.
Kind of like bendy water. Yeah, I get you. I'm just teasing. Okay, go.
Plausible mechanism for that.
Keep going.
So then you test it. You say, well, that doesn't match observation, so it doesn't match the hypothesis, and the hypothesis is not supported. Then the globe hypothesis would be that the sun is to the side of the mountain and the globe is rotating away in relation to the sun, so the light can come up at an
actually
angle.
hit it from the bottom.
And or from a little bit
lower angle, a lower angle, not necessarily in elevation, but in angle or whatever.
Yeah.
See, and then I have an example really quick that's not with the sun, but I've done this on my street just to see, and I don't really understand. I'm not going to say that I know everything about it, but okay, down about a half a mile down my road, there's a stop sign, and it's generally flat road. It's not like perfectly flat, but it's not like a hill or something like that.
Yeah.
I can clearly see the stop sign, and the stop sign's about 8-9 feet, something like that. I think it's above my head. Like when I walk by it, the stop sign's above my head. And if I stand in front of my house about a half a mile away, the stop sign, it looks like it's straight ahead. I can take a mirror and hold it above my eyes, and I can see the stop sign in the mirror.
Okay.
So the stop sign is above that mirror. It's higher than that mirror. How does that work then? Do you know what I'm saying? I don't understand.
I don't think I understand what you're saying.
Let me see. Okay, so let's just draw a picture in our minds. So scratch all that I was just saying. Okay, we're standing on a flat road and we're looking towards a stop sign that's half a mile away. And let's make the stop sign a little higher so that it makes a little more sense. Okay, let's say the stop sign is 15 feet tall.
Okay.
And I'm standing on the road and my eyes are at 5.5 feet tall. So it's about 10 feet higher than my eyes. How can I take a mirror, just holding it like basically right above my eyes, and see that stop sign in the mirror? I'm just bringing it up because it's something that's odd to me. It doesn't seem like geometry can explain that.
I don't see the problem with that though myself. So
it's similar to the sun being higher than the clouds. And but the clouds aren't a mirror. I understand that.
Yeah. All right. So the light from the stop sign goes more than just to your eye.
Yeah.
right? It goes above your
Well,
head.
we have to include that factor that we are part of the observation.
Yeah, you're the
Our
observer,
eyes
but
are.
but
Yeah.
but we know. Sorry, I dropped my marker. We know that the light from the stop sign doesn't just go to your eyes; it goes above your eyes
Kind of like the sun.
and to the
It would
side.
be the same.
Right.
The
So
sun would
so
kind of be the same.
if you put a mirror there, it'll intercept the light that's coming there that wasn't headed for your eyes normally, and then bounce off the mirror and come to your eye. So
How does that happen though if it's above? Like if the stop sign's above my mirror, how does it go whoop, like that? How does it go under? Do you know what I'm saying? And I know it's a very slight amount. If we're talking like a half a mile away, it's basically a straight line at 15 or 5 feet or whatever. It's basically almost the same. But what I'm saying is that's how I see the sun being far away and the clouds being far away. Like a lot of times you'll have clouds above your head and you'll see the sun going over during the day. And then when the sun's going down, it'll disappear behind those clouds, but then it'll come and show up again when it's right on the horizon and kind of underneath the clouds. Do you know what I mean? You'll see it like there would have to be an opening or something in the clouds that lets you see it.
yeah.
Do you get what I'm saying? Or
No. Oh, hold on. I'm being delivered. Why
uh-oh.
is it on a drink carrier? I have a cat on a drink carrier. What?
It's a kitty drink.
So that you don't spill the drinks.
Toon, don't eat it. Don't.
No. I love cats. I just can't eat.
No,
a whole
that's a
one.
cute cat.
This is Turtle. Yep. People
Turtle.
know Turtle.
That's a cute cat.
Um,
That's a small cat. Is that a kitten?
Kitten, yeah.
Okay.
So yeah, he's not meowing right now. He meows a lot. He's a very talkative cat.
I like talkative cats.
So-
My cat's more of a scratchy type of cat. He's scratchy and bitey.
A bitey cat. Yeah.
He might even show up. Or it's a she, actually. I call it a he because he's so mean. But she might show up. She comes down here to my room here and does like demands things from me with claws and bites.
That wouldn't last long. So, what do you want, Kitty? You want to go? Here. See if he'll sit on the chair.
YouTube famous.
Yeah, they know it. They know his name. It's Turtle. We have another cat named Raccoon. So, when it came time to name this cat, they decided to go with the same theme. All right. So I'm still not quite understanding why the mirror sitting up here is a problem, because the light comes to the mirror. It didn't come here and then bounce up to the mirror. It was headed for the mirror.
But the stop sign was let me make sure that you're understanding me. Like, this is a old broken cell phone, but this would work just as well. Like right now, I don't know if you'd be able to see this if I do this to the camera. I can't actually see it. Hold on a minute. Let me get my
Well,
this is probably going to look funny, but like, okay, I don't know if you can see, just like that.
Yeah, I can
So
see the surface.
The stop sign is up here. So my shirt's getting more out, but the stop sign is above this.
Your green screen is
so
yeah.
it has, yeah, I know. So it has to go like the stop sign is up here, and so the light from the stop sign would kind of have to go down and then to the mirror. Do you know what I'm saying?
Yeah. So I mean, you're only going to see the stop sign in the mirror if there's a direct path of the light to the mirror.
That's what I mean.
And you're
so how does that work?
And
because the stop sign's higher than my head.
Can you see it with your eyes?
Yes.
Okay. So then can the surface of the mirror see it?
Yes.
Okay.
Or the reflect or the angle or whatever of the mirror can. Yeah. So the sun does the same thing, right? With the clouds. I'm just saying, like
I don't think
as the sun is
hold on.
is setting. Okay.
I need some help. Hold on a second.
Open a tab, would you? What did you really open though? Because that sounded like a squirt or a Fresca or something. What is it? Cream soda? What do you got?
Yeah. It's creamy root beer.
Oh, that's good stuff.
So I have the remnants of the little bit of I call it toonshine, but it's It's not.
Moonshine.
It's just. It's the same stuff. So just a second.
Yeah, keep sipping it down, Tune. You'll need it. I'm just kidding.
And then off camera, I do this when.
And nobody knows.
But yeah, nobody knows. I try to.
You just said off camera. You just did it on camera.
I know.
What are you doing?
Because you know my tricks.
I know. It's a Minnesota thing, right?
I think it's not just a Minnesota thing.
You know, they say Minnesota nice, and all I ever see is like in the winter, Minnesota ice. Like, there's nobody nice here. They're not very nice here.
Tell you, when it's that cold, it's not.
People are crabby when it's that cold. They're like, yeah, I don't have to repeat what they say. They sound a lot like the people in your chat sometimes. But anyway,
is that a stocking cap or is it a like a baseball?
It is
okay.
Really bleached out from working out in the sun.
Okay.
Hat or baseball hat, whatever.
So we've got a couple people. We've got somebody saying that you look like Fred Durst. You don't.
Don't even start with that.
That is Jason from Mexico.
Because I could start cussing Tune out and be like, you.
That's
but
a different guy.
That just doesn't seem to go anywhere with the conversation. But anyway.
And then somebody called you Austin. John Hawkins said you're Sean Austin Hawkins. because
I'm not Austin.
Austin, though. Yeah.
I'm just a guy. I'm a carpenter that I was helping my dad work today and got all grubby dirty, and then I came home, changed, and yeah.
All right. So I think that somebody said the mirror isn't level. So I think if you were to hold the mirror like
perfectly
level, then the bottom of the mirror couldn't see. Yeah. So when you tip
that makes some sense. Like if I'm like this, I can't see it because it's above the mirror or above the reflection. But if I go like that, right? Is that what you're saying? Kind of fold it.
Yeah,
like
you got to tip it a little.
Okay.
So
that makes sense.
All right. So I've got just a second here. Here's my microphone. Just a second.
My ears. Knock it off. Just kidding.
I'm gonna move it down here.
Not that bad.
There it is. Got it. Okay. So, and I make sure my levels are fine. Doop. Turn myself up
levels.
A little bit. There we go.
Levels, eh?
There's multiple definitions of level.
Yeah, apparently it's curved.
It is. But contrary to what's
only
what's his name?
If the Earth was curved, right? What if the Earth wasn't curved? Would level be curved? No, it wouldn't.
Well, no.
If the Earth was flat, level would be flat.
Absolutely.
That's all I'm saying.
Absolutely.
If it's curved, it'd be curved. That's great.
That's the thing about the definition, right? The definition is just a definition. You need measurements to confirm the definition.
Oh, let's talk about measurements. That was one thing during your last, your previous, today debate. That was an interesting one, for sure. Very interesting. I didn't really understand that one. A lot of that one. I was just listening.
He was struggling.
I was struggling. I can't even chat right now because it says sign into chat. For some reason, my computer updated last night and it keeps continually signing me out. And I did all the catch and cookies and all that stuff, and still it's doing it. So I was fighting with that the whole time.
Do you guys hear the cat meowing?
I hear you meowing now.
Yeah. All right. Professor Phil Bell says you sound like you're curious. So take that as a compliment.
Oh, yeah. That he actually thinks the Earth is flat. It's actually not that I think that it is. It's just that I have measurements of it being flat. And actually, I want to talk to you about that. Hey, what's a null vector? What's a null vector? If we were talking about flat or curved, what's a null vector or a zero vector?
Would that be the magnitude of the vector is 0?
Yes, it would be. I wrote it down here. Okay. What I'm saying is if you have something flat, it is not positive or negative from that 0 vector of being flat. There is no measurement of flat. It would be 0, and a vector that's multiplied by 0 is 0.
So, all right. So to measure flatness,
you wouldn't measure it. You would measure.
No, you can measure it. You take something that is flat, right? So let's imagine here. This is my slide rule, right? But
okay,
it's flat, right? It's straight. So you take this is a physical thing, but you can't easily do something long enough to measure the shape of the Earth physically. But let's instead use optical measurements. So you'd say, all right, well, so from here to here, we need to correct for atmospheric conditions, and we're going to go from here to here, and we're going to measure the amount of deviation from this flatness.
Mm-hmm. That would be the measurement.
Right. So if it goes like this, if it curves down, then that's a deviation away from flatness. So it's a measurement
it's a negative
of
deviation.
not. It's a measurement of not flatness.
Yes.
So a measurement of flatness would be, okay, so over 1
0.
mile, 2 miles, 3 miles, 4 miles.
Didn't curve.
Exactly. Within the margin.
That would be absent of a measurement, wouldn't it?
No.
So what would the number be? What would the number be?
I want to be clear.
Okay.
Within the margin of error of the measuring device.
Yeah.
That's an important part.
And we can even be more general than that. I'm not going to get picky on anything like that. You know me.
People,
but what I will say is, what's the number?
People clip my videos. I need to be careful. So the number would be 0, and 0 is a measurement.
Okay, so when you bring up, and I'm just picking on you here because you pick on the flat earthers all the time. And you say, do you have, like in the last debate, you say, so what is your measurement of flatness? You gotta have a little more integrity than that. I honestly think, because
it's a
what
trap.
you're doing is what you're doing is
I'm on it. I'll tell you right now, it's a trap.
No, I know.
Because I know there's no
but,
measurements of flatness.
Yeah,
there's no measurements
so
that
I just
support
had to explain that to you, and you were still kind of trying to fight against it until right now you're like, okay, fine, I admit it.
No, I admit that I know that there are no measurements to support them.
No, there's no measurement. The flat table in your kitchen, the measurement of its flatness, it doesn't have a number. It's just 0. It doesn't go up or down from that flatness.
But 0 is a number.
That's what I'm saying. It is 0 every time. Anytime that you're going to try to measure something, or you're going to ask someone for a measurement of something flat, it's going to be 0.
Okay.
There is no other measurement of flat.
I have to evict the cat. Just a second here.
No problem.
It's too noisy.
Uh-oh, I might have to steal Toon's screen there. No, I won't. I was going to steal your screen, and
last night that cat was wearing a dress, just so you know.
Oh wow, cat dress. That's interesting. You must have children, girls, maybe.
I do. That was my daughter. Yes.
Okay, I could have guessed that.
Okay, so it is possible to have 0 be the result of your measurement. So you could say, here's how you could get in a whole different way. Just as an example, you could say, well, I'm going to measure out a ton of iron. So you go measure a ton of iron on a scale or something, and then you take that ton of iron and you bring it somewhere else and you put it on a scale. So you don't have the original scale. You have somewhere else a scale.
Yeah, another scale, a secondary, another scale. Okay.
But this one is a ton, right? It might be better to do
according to the first scale.
A kilogram. And so
whatever it is.
Put on here, and then you put something else here, right?
Yeah.
And here's our balance, and it's not there. And then you keep adding
till you're at a ton. Okay.
Right there. Now, what is the difference in mass between these two?
0.
It's still a number. It's a measurement.
It's a measurement. It's a measurement. It's a number. Yeah. But to ask someone for it is not make any sense. That's what I'm saying.
If the Earth were flat, you could do it.
No. But listen, if I think the Earth is flat and the measurement's 0, like, let me think of an example. If there is a table in your kitchen and it has no food on it, how much food does it have on it?
0.
There you go.
That's
the kind of question you're asking.
That's a valid answer.
Yeah, but you're
that's a numerical answer.
Okay, I'll chalk it up to this. It's funny for the globe, for the competition, or the jokes that go back and forth, or what do we even call that? Rivalry, or whatever we call that. That's what it is, right? Can you admit that? That's what it is. It's like for fun that you say that.
It's a game.
So what number would you actually expect to hear from someone?
If the Earth were flat, and you were to do a measurement over a mile,
maybe like a Mille Lacs Lake,
right?
Yep.
You would use a measurement device, and then you'd come up, and your number would probably not actually be 0. It would be close to 0, and the margin of error of the instrument, when you include that margin of error, 0 would be included in the answer. And that's what I'm looking for. So like when I cite Jesse Kozlowski and his measurement, he has a measurement across the lake where he set up on both sides of the lake a target, a theodolite target on both sides, and he used the surface of the water and he measured above the surface of the water.
At the edges of the lake?
Right on the edge of the lake, yeah.
Okay. And
he set up the target on both sides at the same height. And he measured across it, and it was 0.15 feet. It's so weird to use this unit for this type of measurement, but I'm expecting metric. But 0.15 feet of drop from one side to the other, and then he did the same on the other. He did both sides, and both got 1.15 feet.
Can I ask you a question about that? Or I'll let you finish.
I'll finish it. It was 0.48 miles apart. So just under half a mile.
0.15 is that, what's that? That's 3 inches, 2.5 inches? I don't know exactly what it is.
It is 1.8 inches.
1.8 inches. Okay.
Yeah. Let me run that again.
So I do have a legitimate question about that.
Yeah.
On any surface of water that's outdoors, there's going to be different heights of, especially if you're over a half a mile like that, you're going to have different levels of water within that body of water. So if there right now, if there's water between me and you,
isn't water always level?
Not when there's swell and waves and wind and heat and cold. It's always moving.
Absolutely. Yep.
But I've done this on Lake George. It's only a mile across, and I've done it with my P900, and I've tried to see the look across, because with the P1000 or P900, you can see really good a mile. Like you can really see the dock and the rocks and everything. But you can't ever see the surface, unless it was glass smooth. You're gonna have what are you going to see when you're looking across? You're going to see the highest point of water. So if there's any wave, that's the one you're going to see in that 4.5 miles, right?
But he wasn't measuring he wasn't looking at the water. He wasn't measuring to the water. He used the water as a reference. So down at the bottom, so
he had a specific height above the water.
Yeah, let me pull it up.
Theodolite. I think I know what you're saying. And so that measurement, say it was 40 inches or something on each side, that was what he expected.
So he actually drove. I'll bring it up. He drove 2 nails into the water.
I thought you were going to start talking about Jesus for a second. He drove 2 nails into.
No. So, all right. I'll share this to you so you can see it, and then everybody can see it.
All right.
There we go. All right. So this is the site here, and here he starts out with this is the view through the theodolite, and you can see the center of that target is the same elevation as the theodolite that he's on. You can see it's a bit above it. But let me get down to, this isn't the part I was talking about. He shows how he actually set up the reference. So here's his section that he was looking across. Here is the level that he put across 2 stakes here that he put in the ground. And he measured the height.
Oh, I think maybe I've seen this a long time ago on your channel, actually. I think you went over this one time.
So there he measured the height above the ground, so above the water level. So he knows how high the top of that stake is.
Minus all the variation in the water that you can see right there. There's inches of variation right there in that small picture. But Yep.
And so, again, that's every measurement. And Nathan Thompson doesn't understand this. A lot of people don't understand this. Every measurement has a margin of error. So here he's showing as an example This isn't the actual measurement. This is a picture of him doing an example of the measurement.
Getting a height, yeah.
Bev has a hard time understanding that this particular photograph isn't the actual measurement.
Where's even the water?
This is a, yeah. So anyway, so there, that's how, and you can see down at the bottom here, the little piece of wood.
Yeah.
And that's
where the levels were, or the level was.
Yeah. And then he set up, this is a GNSS receiver, or we call it GPS usually. And then there's his theodolite, and he set the height of it at a specific elevation above the water. He did the same on both sides. He has this level here.
Yep. And see, to me, this how do you know like if you go halfway between the two theodolites, how do you know what the surface of the water is at right there?
He didn't use that as the measurement. So
I'm not understanding how he did it yet. I'm sorry.
So I'll keep going. Just the point of this right here, just so we're clear, is that he measured above the surface of the water.
Yes.
Okay. Then I'll get down to the actual, here's the actual measurements. 0.15. You see this?
Yep. I can see it.
Curve drop from horizontal plane at standpoint. So, and here's the picture. This is the important thing. The picture is the description. You can see the curved part there.
Mm-hmm.
That's the surface of the water. He didn't measure.
How did he know that though?
He didn't. It's just a diagram. He did not measure to the surface of the water. So what he's doing is he's showing a curved surface.
On these paper, right?
Yes. And then that horizontal plane, you see a horizontal plane from the left side to the right?
Yep.
So, and it's greatly exaggerated.
Yeah. But
the theodolite measures, taking into account refraction, of course, and we can get to that in a bit. Minus refraction, it gets that horizontal plane, and then there's a drop. So you point the theodolite straight out at 90 degrees zenith, and then then it's farther down than that. To action, and that's the drop that he's measuring. It's an angular drop, but because he knows the distance between the two of them, using trigonometry, you can know the actual linear drop that's happening.
What kind of apparatus does the theodolite have to what are the margins of error on leveling it?
It's a good question, and being that he is a licensed geodetic surveyor, so he
could use the surface of water to level it.
He did use the surface of water.
Good.
I'll show you.
Okay.
Again, it was right here. This is where he used the surface of water. So he used the surface of water half a mile apart at 2 points.
Mm-hmm.
So going with water is level, which we both agree water is level, and we both agree, because we talked about it, if the earth is flat, then level is flat, and if the earth is a sphere, then level is curved. So he's using the surface of water, but
he's not measuring the actual surface of the water.
He's not looking at the surface of the water to measure it.
He's looking at the angle.
He's looking at a point above the surface of the water.
Yes. And because I use levels all the time and lasers all the time, and like laser levels for installing things.
And that's different in construction.
No, I know. I'm not saying that it's like as precise or anything. What I'm saying is I'm curious about the theodolite, how accurate. You can't just pick a point and get something perfectly level. Like that takes, I don't know how you would do that. We have a lot of equipment. Like you can buy a $500 DeWalt laser level, and it's off a certain amount.
Yes.
So you can level across, but if your line is pointing at where that diagram showed where it was increased upward, then I think that first of all, that's probably not the best way to find out whether the surface of the water is flat or not, or whether or not the space between those 2 points is curved or flat. I think that's probably a hard to get level line.
How would you do a better job and not introduce more problems with refraction? absolutely.
Oh, you actually, I didn't listen to the thing you just said.
Without introducing more difficult to control confounding variables. That's the problem.
I don't really think you could. And that's the interesting thing about this debate is there are so many things that we do look at that are like this example right here is a great example. And I'm not ripping on his observation or anything. What I'm saying is, in my understanding, to pick a point and to point somewhere and think that you're pointing level, it would be like pointing up at the sky towards zenith and thinking you're pointing plumb. It's very hard to find that precise point of level or not level, or plumb or not plumb.
A theodolite is an instrument specifically designed to do that, so it's very good at doing
it's
that.
probably the best way to do it as far as, but yeah, half a mile, that's not very far either. But like you said, you introduce more refraction and things when you go farther.
It does, but he did the very same one on this very same website at about 1.5 miles.
Okay.
So and it looks the same when you get to it. You can't quite see the difference because the setup is the same. I think it was a different.
I got my
day.
cat this time. You gotta see this cat. This cat's awesome. This is Bobby.
All right, hold on.
She's kind of scratchy and bitey, but she's like relaxing now.
Oh, there you go. Another tabby.
Yep. She's got no tail and she's got really sharp claws.
No tail.
She just showed up one day.
Just showed up.
Yeah, just showed up.
Nice.
And I brought her to the vet. I'm like, this cat just showed up at my house. I want to get it fixed. I don't want kittens. And they go, this is like a kitten. It's less than a year old. And they went to fix her and she had a tattoo like she had already been fixed. Oh. And they were like, that's weird because she's so young. They could tell by her teeth or something, whatever. So no kittens. That's a good thing.
That's good. All right, I want to address something. Eyes Open says you should be able to replicate the same measurement in a bathtub. Distance is irrelevant. The properties of water do not change. You're right. You absolutely could replicate the same measurement in a bathtub. The problem is finding the instruments that are sensitive enough to do that particular measurement, because over 1/2 mile.
Shout out, Be the Change. Sorry to interrupt your tune.
No, we don't.
I just have to say hi to Nathan Thompson. I just have to.
Do you seriously still? I mean, he stole money from Austin. I mean, I'm not.
Everybody says
fan
what
of
they
Austin,
say. You know what? I don't get into the. I'm just being honest with you. I don't get into the drama, man. People have things happen between them and they part ways and whatever happens. But I would have to say that time changes all that too. Time kind of forgets some of the stuff that happens and people forgive each other or people, whatever. I'm just saying like that if you focus on it, you can do that all you want, or make like with Jake, the asshole. I think like, I'll give you my honest opinion about it, Tune. You could do, you've done better videos. That's all I'm saying.
Than Jake's?
Like, all of that was
a quick throwaway, like poking fun at a low-hanging fruit Jake.
It kind of puts you in and excuse me for saying this, I'm not trying to rip on you, but it kind of puts you in like a sleazy position from the outer looking in. That's what I'm saying. And I'm not saying that to be mean, just saying my opinion.
I get it, but it was too sweet.
I saw him doing some. It was Squeaky, or what's that guy's name? You know who I'm talking about? The guy with the earrings and the accent.
Creaky Blinder.
Creaky Blinder. No, I said Squeaky. Creaky Blinder made a video about him, I think, and that kind of maybe started the whole back and forth thing.
It was Simon Dan did it.
Simon Dan. Okay.
Creaky did it, and then I'm just riding their coattails.
Yeah, you're just like riding the wave. No,
whatever.
I
thought it was funny. Here's the deal. Here's what I did, and Jake totally missed this.
Entertaining, right? Entertaining.
It is, and I got to remind myself, this is entertainment for smart people. I don't.
And you know what else it is? You know what else it is? It's entertainment for people that are just like that have come into this subject. Like, why are people talking about a globe or flat Earth all of a sudden? Why are people talking about this? Well, it's fun to have some fun. right? Me and you, totally disagree. Totally disagree. But like, I consider you to be kind of harsh with some other people, but you're pretty nice to me. So it's cool. Probably because I'm in Minnesota, you know, I'll come and get you.
Yeah.
By the way, I remember in the chat, I don't know if you saw it, but Mallory was asking for her sweatshirt.
Oh my gosh.
I told her that if you didn't get that sweatshirt out there, that I'm gonna come and beat you up.
Totally do it. Yep.
So
here's what
that going for you.
What I did. Here's the challenge with that.
Okay.
I put, and it's a terrible excuse. I got a temporary credit card, an anonymous credit card, and I just put some money into that, and I use that to place the order. So I just have to go look that number up. Not that it's hard to do. I have it in Evernote.
That's an old app. I'm just kidding.
Oh, I love Evernote.
Mallory would probably appreciate it if you just got off your tail and did it.
I'm sorry.
Just letting you know.
You're right.
I'm just teasing.
You're right.
You know that. Another thing I want to bring up is 8 inches per mile squared. Let's talk about that and Pythagorean theorem, because I've done the math myself and I get the same exact numbers doing 8 inches per mile squared. But I only to a certain distance.
Let's
talk about that.
Do we wrap up this one yet?
It's up to you. I'm totally open to whatever. I am.
Here's the deal. Then that is
you just told that last debater, right? Am I right that you just told him no? It's not 8 inches per mile squared. That doesn't give you the
give me a second on that
drop.
Let me get previous. I showed what I expect when I say show me a measurement of flatness. I show a measurement of curvature.
Because there's a measurement of curvature.
Yeah.
I mean, in your for curvature, there would be a measurement, right?
If the Earth were flat, that same test would come up with
0.
It would have no drop.
It would come up null or 0, one or the other, however you want to say it. Okay.
So I will. So here, 8 inches per mile squared. And Nathan is in the chat, and I hope he watches this part too, because it's a good thing. And 8 inches per mile squared is the right approximation for its intended purpose, but its intended purpose is not showing the amount of obstruction. That's not
showing
its purpose.
The amount of from your line of sight down to the surface of that curved surface.
Nope.
A drop, right?
It's showing drop between two things that you can see.
Your line of sight to the surface.
Yeah, and so
you go out 5 miles, and then that line of sight is going to be higher off the surface if it's curved.
Yeah, and I'll go back to this because this shows right here, this diagram. This shows it says drop. That particular spot there, that's drop.
That's what it measures.
That's what correct. It gives us. That is the right spot to use 8 inches per mile squared.
Okay, so I want to do this. I want to do the math really quick, or I'll at least explain the way I did it. And I want to show you that you shouldn't say that to flat earthers, because it makes you look like very biased towards ganging up on them.
I'll explain. It is still the wrong measurement, because that has nothing to do with what should be obstructed.
Okay, can I just go over in my head, and you just hear me and say maybe point out where I'm wrong or where I might be thinking of it different. Okay, the way I think of it is there is a center to the globe. If it's a globe, there's a center, and from that center up to the surface is whatever 3959 or something. Okay, and my camera is say 6 feet above the surface. So we're at 3,959 miles and 6 feet, right? Take that number and use Pythagorean theorem, and you will get the exact same number that you'll get using 8 inches per mile squared within like a small margin of decimals.
Yeah.
So to me, when I did this on my own on a big dry erase board, and because I really wanted to know exactly what that formula actually showed us, I came up with the exact same numbers doing the math myself. And this was like decimal points out to like 15 decimal points.
Here's the deal. Here's for drop. It is the correct formula for drop, but it is
People
not
are thinking
it is not the correct formula. It's not it's not the bulge, and it's not the amount that is hidden. And that's the straw man. because
the way I look at it is
all the flat earthers use they say 8 inches per mile squared, and they use that wrongly to predict the amount hidden. So
I don't
I'll
think
show
they
you.
always do, though. I think maybe some of them do that don't understand. Some of them say per square mile.
Yeah, I know. They
what I'm
can't
saying
even
is
get.
some of them don't understand it, but the ones that I consider myself to not be like that, I'm not going to talk about something or make a claim about something unless I actually know what I'm.
So,
you know what I mean?
So
and the numbers, when I go over the numbers, they work out perfectly.
But
so
not for drop.
It does work for drop.
Sorry, just for drop, not for
just
amount
for drop.
hidden.
Here's the way I look at it. If you're on a sphere, you're always on the top for some reason, but I'm always on the top for some. The person perceiving is always on the top, so it drops in every direction. Right. So that's how we measure that drop.
Okay, let me go over it. Okay.
Okay.
And Nathan
I'm only bringing up some things I've heard you say over and over again. I'm like, come on.
And
come on, Toon.
This will explain. All right, here I have. Can you see this? I think. Oh no, you can't. Hold on, you can't. Wait just a second. I need to share. I need to switch my camera, and you will see. I think you'll see a different. You'll see it upside down. All right. Do you see my paper?
Okay. Here? Yep, I can see it. Yep.
It's because the camera there is upside down to everybody except for you. So.
Okay. That's fine. So, actually, it's upside down for me too. So maybe it's right.
It's right side up for everybody except for you.
Okay.
So
I can figure it out.
There's the surface of the Earth.
The concave surface. I'm just kidding.
So this is the geometry for predicting drop. Okay.
Yep.
So here you're up on some surface here.
Yep.
Here's you, and there's your eye, right? So now you have over here some structure that is,
and you have your line of sight coming tangent with the surface, so I'll seeing the other object, and it's that drop at the line of sight at the distance. I didn't
make this. I got to make this taller.
Oh, just use a little refraction in there. It'll work.
So there
it has to be tangent with the surface, right?
Right there.
Or is it to the surface? How do you say that right?
Okay, tangent at the surface. So there's a point somewhere in here.
Yeah, that's where it's touching tangent. Or whatever. Yeah.
So
that would be the horizon in your model.
The
right?
drop, the amount, the 8 inches per mile squared, people say is wrong because it's parabola. That's incorrect. It is fine to use as intended.
Because of the distance, nobody's making an observation that would be far enough where it wouldn't work.
Exactly. The problem is not that it's a parabola. The problem is that there's no way to take into account the observer's height. It is strictly for an observer's height of 0.
Not this.
8 inches per mile squared works right here.
8 inches per mile squared works from wherever your line of sight is.
It only works from here. It's only.
What do you mean? What do you mean from there?
Because it gives you drop.
No, you're saying your line of sight has to touch the surface, basically, is what you're saying.
Yeah, but here's
I get what you're saying.
8 inches per mile squared works from here because this drop here is going to go down. Is what surface. It can give you this drop.
Yes, that is what the Pythagorean theorem or
from here,
that 8 inches per mile will get you. Yes.
From here, not from here, just from here.
But your line of sight determines where that tangent is.
Yeah. But
you get what I'm saying?
It doesn't take this into account. So how do you take this into account?
Because your line of sight is tangent.
It is, but you need to get this height somehow. How do you include this height?
And you always do if you were on a if you were standing on a sphere, you're always going to have that tangent at wherever distance.
And it's right there. But how do you take the observer's height into account in that formula?
Because it's a straight line of sight. It's not a curved line of sight. It's not going up and then down.
8 inches per mile squared only works from here where your vision is half obstructed by the water, basically. So there's a way to include this.
If you wanna see what I'm saying, so take your fella there on the mountain and put a guy on top of him. Okay, put a guy on top of him, and so he's standing on his shoulders. Now draw your line and make it tangent with the surface, and you're going to see what I mean. It is definitely including the observer height, because now you're going to get a different height.
Yeah,
because you're at a different height.
But
why don't you? If it's only from that center point, why don't you get the same line then? Why don't you get the same number and the same line?
That's the point. You can't use 8 inches per mile squared for both of these people.
Yes,
because
you can.
They're going to have a different, this one's going to have this much obstructed, this one's going to have this much obstructed.
Because one of them's taller.
Exactly. They're both going to have a different amount of obstructed based on their elevation. So how do you, but if you just use 8 inches per mile squared, you've just agreed with me that the elevation changes the amount obstructed, but how do you take that into account when you just say 8 inches per mile squared?
Because your line of sight is straight. It's a straight line that you're drawing out from yourself.
I
think you're confused.
I'll explain it. No, I understand the geometry. I'll show you how to do it. Okay.
All right.
You need to, all right, I'm going to restart
anytime
this.
the observer height is different, you're going to see a different amount of that building on the other side.
And
so that's how the observer height is it does include, or that's one of the variables is the observer height.
Yeah. And so how do you take that into account?
It's already taken into account when you look and you see that tangent line with the surface. That is,
but how do you mathematically take that into account?
What do you mean by how do you how do you put numbers to it?
Or when people say we see too far, and then they use 8 inches per mile squared.
Yep.
How do they take into account the observer's height?
Well, you're saying like in numbers, you mean?
Yeah, when you do the math, when you're like, well, because you
let's say that
it's a hypothesis prediction, right?
Yeah, we can do that.
The prediction, there's a prediction for how much is obstructed. Now somebody
using
said
the Pythagorean theorem, you can get the observer height if you know how much of a building you can see and you know the distance, because your line of sight's always going to be straight.
We're going to do the prediction before the measurement here.
That's what I mean. You can, and it'll be consistent.
Okay. So how do you take the observer's height into account?
Or you got to give me some numbers or something. I don't know what you mean.
Let's say the observer is
right there,
20 feet high.
Okay, his eyes are 20 feet high.
Yep.
Okay.
And you take 8 inches per mile squared.
How far is he looking? We need these numbers if you're going to be okay. How far is he looking, and what is the drop at the point where the building is at that distance? 30 miles.
Okay. And we've got what would I say? 20 feet?
No, we're trying to find that out. We don't know that.
No. We're
trying to find out the observer height.
Coming into this. No. We're not trying to find out the observer height. We know the observer height when you do the measurement because the observer was there. They know where they're at.
Yeah,
they know how high they are in relation to the water.
I thought you were just saying that you couldn't.
Let's say we know that to be 20 feet.
Because I can do the math and I can tell you how much drop there should be there. Is that what you want?
So what's the math to predict the amount hidden for the globe? What's the math to predict the amount hidden?
A squared plus B squared equals C squared, right?
So you're going to make a triangle.
Yeah, your triangle to the center of the Earth. So from your observer point to the center of the Earth to the tangent point.
To the center of the Earth down here?
Yeah. That's how you do the Pythagorean theorem.
Okay.
Go down to the center of the Earth. So your observer height is 20 feet. So you have 3,959 miles and 20 feet.
Okay.
That's your observer height. That's one of your legs of your triangle.
Okay.
And then your line of sight is that a right triangle though? So let me that's your line of sight, because it's just like
to here.
It's not to scale. No, the observer is standing from the center of the Earth. They're standing in a straight line above and they're looking at 90 degrees out. And on your paper it doesn't look like 90 because
they're not looking 90 degrees out.
89.997 or what?
Well, yeah, there's a dip. There's always a dip.
No, but you get what I'm saying. So if it's 90 degrees, you're saying it would end up looking up in the air.
Yeah, here is your 90 degrees zenith, right?
But that's not actually what happens. And then I know what you're saying.
There's always a dip.
Okay, so your line of sight, let's say your building is 30 miles away from your eyes.
Yep.
So that leg of the triangle is going to be 30 miles. So you have 3,959 miles and 20 feet plus 30 miles, and this you'd have to square both of these. So, and that's why I'm saying the numbers get to be kind of big. I had to do it with calculator.
Okay.
And I had to write the numbers down on my board as I did it because they're really long numbers. So what's 39? We can do the math if you want. You got a calculator right there. Hit 39. How do we do that number? Oh boy.
Well, before we do the math, let's write out what we're going to do.
Okay.
So we have from the observer height to the center of the earth, and we have this distance here. Now what?
Now you're going to, from the center of the earth to the building that your line of sight touches, that point where your line of sight touches the building. Yeah, you can draw a line right from there down. Okay. And you're obviously not going to end up looking like a right triangle, but it is a right triangle if you're looking out and this from the center of the earth.
But it's not a right triangle unless
you're a right triangle.
It's only a right triangle if you are
on paper. It's a right triangle. I'm not saying that your eyes are looking that way, but your tangent, your line of sight when it touches the surface, obviously is not 90 degrees, is it? That's what you're saying right now. And I'm not, because you're 20 feet in the air. So that 20 feet over 30 miles, that's the angle that'll be different from 90 degrees. But the center of the earth is a concept place. And so you can make it 90 degrees, then you can make it work. Yeah. I mean, what I'm saying is it works the same way.
This angle, there's only one way to make this angle 90 degrees. That's to be 1/4 of the way around the earth.
That's not what I'm saying.
Okay, so
from the center of the earth
where's the 90? Where should I draw the 90 degree?
Let me just give you the numbers and you'll understand where the 90 degrees is. Okay, a squared we'll say is 39, 59, and 20 feet, however we want to write that down. Or that would be a. So we'd have to square that number. A is 39, 59 plus 20 feet. So we have to square that.
Okay. And what's B?
And then the B squared would be 30 miles squared.
Okay.
And those two added, two squared.
What's C?
C is from the center of the earth to, and I hope I'm doing this right because I am looking at it upside down. But there we go. Okay, so yeah, A squared plus B squared. Oh, I'm doing it wrong. The line of sight's going to be C. I'm sorry. Okay. Because I think, and you can help me and tell me if I'm right. I haven't done this math for like years. So we'd have, let's say C is 30, A squared plus B squared. You know what? I might even have the paper I did it on in the other room. I might go look. But the way I'm looking at it is the center of the earth. It would be, I'm sorry. The 30 miles would be B. I'm sorry. So the 30 miles would be B and C would be the imaginary line from the center to the point at the building that your line of sight hits. Does that sound right? Or am I getting the legs of the triangle wrong?
Well, there is no right triangle that you define there.
It's very close to right triangle. It actually is a right triangle because the center of the earth is not a place you're going to mark out. It's a concept place. So we've got. It's actually just geometry when we're talking about a circle. So this is a chord across, across there, right? Is B. So A, B, C, but that's not a right triangle. No, that's not a right triangle. So when I stand, I can show you where the right triangle is in this formula. Yeah, maybe I need to refresh the course. Is here. Where's the right triangle? This is the triangle actually. That is the approximation. Okay, that's not how I did the math. That's not. I don't think that's A squared plus B. I mean, I don't think that's 8 inches per mile squared. The picture, the meme that flat earthers constantly post of the drop
formula, a squared plus b squared equals c squared. This is what, I'm going to scratch this out because that's not right. That's not right. So it's not confusing. This is what they do, and then they have the picture, right? And this is correct. This is the 8 inches per mile squared.
The viewer height has to be is included in that because it's a straight line of sight.
But the formula, this formula here.
I got to get a piece of paper and write it down just so I can, like, I'm not able to think about it clearly here.
This formula right here, where do I plug in?
Oh, sorry, I'm grabbing I gotta just draw it out on paper for myself here to see what I'm doing here.
So that formula, 8 inches per mile squared, the claim is equals h, hidden height. But where do you put in the observer's height in this formula? Because we know the answer is going to be different at a different elevation.
Yes, and your angle of your line of sight is going to also be different. So you're going to see a higher or a lower point on the building because your observer height is higher or lower.
But this formula doesn't include the angle of the observer.
It does.
Where do I put that in this formula?
The way I did it was, you know what? I think I'm giving you the wrong info. Okay, so our 39, 59, and 20 feet is going to be the, well, I guess either one, A or B. And your line of sight is going to be the other one. And the drop, I'm sorry. Yeah, that's what I had wrong. It's not the distance, it's the drop from your line of sight down to the center of the earth again. I'm sorry. To
the center of the earth.
Yeah, like where it hits the building up in the air there, right there. Yep. From that down to the center of the earth, right?
Okay, so from here or from here?
Let's see here. I'm just trying to figure out here. Okay, so if we were at the center of the earth and we drew a line up to the camera, let's just say. So it's our 39, 59, and 20 feet.
Let's start over here. So
yeah.
Okay.
So if we just draw a circle, we can just do a geometry. We don't have to do it like it's the earth, but it works the same. If we have a circle and we draw a center point on it, and we go from that center point up to 6 feet above the circle, say where our camera
let's stick with our 20.
Okay, 20. Yeah, yep. 20 feet above. So that's going to be the first. I don't know what they call it, a leg of your triangle, or do they call it a chord?
It's a leg.
Okay, and then 90 degrees out from that, and it will be exactly 90 degrees that your line of sight is looking. And yeah, it may appear to go up in the air on your drawing or in the idea of a circle, because that's what it would do. So that 90 degrees ends up gaining elevation the farther your line of sight goes, correct?
Yeah.
On a circle here. This is just geometry. So now that line of sight where it's hitting the building, or I guess that's going to be hard to do.
Should I draw a line of sight?
You already did.
Where?
You already drew your line of sight.
Where's the line of sight?
The line of sight is the straight line that
this one?
Yes.
But you won't
90 degrees.
But you don't see the building.
You're not to scale there, and you're drastically more curved. Okay. That you're just do geometry. Forget about the surface of the earth and the building.
Okay.
Just draw, maybe grab a new piece of paper. And this is what I'm doing. I can show you here. See mine? Very simple circle.
Okay.
Do you see the center point? And then actually, I'll try to hold this and do that. I don't know if you can you see my camera at all?
Sure.
Can you see what I'm doing?
Yeah.
Okay. So this is the center point. And from here up to our 20-foot elevation is 39, 59, and 20 feet. And then perfectly right angle going your line of sight looking out. That's going to be a squared and b squared. And then you're going to have right here is going to be c squared. Okay.
Okay. I've got it. Yeah.
So this one plus this one equals this one right here.
Okay. But that's
there you go. That's perfect.
And that is the problem is though, that is for a point tangent to the surface.
Yeah. Anytime you look on a curved surface, you're going to have a tangent point. That's the whole
but the problem is that but the observer's over here.
Then that will be where the observer is. Then you draw your line from the
So
center of up to that observer. Okay. And
but
if you go a different
this,
height, you're going to see a different.
But that is what they see. That's what's happening. So we
What do
need
you
to we need to get this to happen, because
you
this
can do it both ways, Toon.
this triangle that you defined is correct,
Yes.
but only for tangent to the
Not
surface.
from the
there.
tangent point. Your tangent, it doesn't, you're okay. If you're looking, if I'm standing straight up, like perfectly plumb, and I'm looking perfectly 90 degrees out, there's no tangent point to my line of sight. It doesn't hit the surface.
So that's what you're talking about.
Yes, and that's exaggerated, so that line isn't going to hit the building. But what I'm saying is, you're there is never a tangent point in your line of sight if
But
you're
when
looking 90 degrees.
When you're talking about the amount hidden, when you have to do,
we don't need to be talking about the amount hidden. We're
that's
talking about
what
the drop.
That's what this formula is about. The problem with this formula is that flat earthers use this formula to predict the amount hidden.
You think
they
flat earthers do that? Maybe some do. Maybe some do. But am I doing that right now? No.
Okay, but
so what I'm saying is, there's a legitimate way that I am aware of. So talking about flat earthers that aren't aware of it and that think that they're going to get a number from something they can't get a number from is irrelevant. What I'm saying is there's a legitimate form of geometry here, and it's not only from that tangent point. You can do it that way, but you can do it from the observer height, 90 degrees out. You're not going to hit a tangent point on the surface, and then you get your drop.
That's fine. That's for drop.
That's called math. It's geometry.
But
it's very simple.
I've never seen a flat earther talk about that.
What
I see
anybody talk about it
is flat earthers say, I see too far, and here's the math saying 8 inches per mile squared says this, and therefore I see too far.
Let me give you the benefit of the doubt.
Without
taking the benefit of the doubt.
Let me finish the thought.
I'm sorry.
Without taking into account the observer's height, and I'll show you how to do that when you're ready.
Okay. All I want to do is give you the benefit of the doubt that I myself have witnessed the same thing you're talking about. Flat earthers determined about it and that don't understand really the numbers that they're putting out, but they're saying, so I'm not saying that this doesn't happen. I'm in agreement with you that they do this, but I also would have to say that all the people in your chat, there's a lot of people, flat earthers and globe earthers, that are pretending they know things that they don't know, or projecting numbers out there that they have no reason to say these specific numbers unless they've done the math. Like you and I are actually doing some of this right now, and you showed me one way and I showed you that it can be done another way, just with a 90-degree triangle or a right triangle, and it gives exact numbers.
But yours was for drop, not for hidden.
Yeah, I don't know. Okay. I don't know. Okay. The hidden would only be, that would have to be with the tangent point, with the surface.
Yeah. So all right.
But you can get that from the drop, can't you?
You can, but it takes two
steps. Like you were saying, your triangle moves over to the.
It takes 2 steps. Let me show you the 2 steps.
Okay.
First step, you need to get this right here.
We already have that.
Once from the observer's position to the tangent point, you need to get.
Okay. And that I don't know exactly how to get that.
When I tell you it will be very familiar to you. I promise. Okay. You watch. Then once you have this point, then you can use 8 inches per mile squared to give you this drop.
So there's kind of 2 ways to use the 8 inches per mile squared. You're saying use a right triangle Pythagorean theorem for 2 different things.
8 inches per mile squared gives you the visible drop. If you can see both, if you can see what you're looking at, and you know the distance, it will tell you how far the drop will be. And that's where Jesse Kozlowski used it correctly on his observation across the lake, because he could see it. Yeah. Nothing was obstructed. He wasn't using that to predict how much was obstructed. So
no, he was just basically drawing a straight line that was as close to level as his equipment could get.
A horizontal. at
Or
that
yeah, I should
point.
say
It wasn't
horizontal.
level. It wasn't level.
Not level. I meant
Yeah.
horizontal.
Okay.
In your world.
This distance here.
Yep. Which doesn't necessarily actually well, I guess that's not a line of sight. That's looking down at the ground, right?
That's to get your distance from the observer to the point of the horizon. Do you
The
know
observer
that?
height there.
I gave you a little hint right there.
I can't see what it says. 22. What does it say? 1.22. Yeah, I know what you're talking about. There's another way to get the observer height.
This distance right here. This has nothing to do with amount hidden.
It has to do with the observer height and the line of sight being tangent.
The distance to the horizon, 1.22 or 1.225 times what?
I can't remember.
This is neglecting refraction. This is without refraction.
Yeah, just like on geometry, you're saying, just straight geometry.
This formula here.
1.22 times the square root of the observer height.
The observer's height in feet.
In feet, okay.
So this you've certainly heard before. If you've heard that, Austin, if you've heard Austin talk about that,
I've heard Austin
Eraser. This comes from Andrew Young and other places.
Does this work? This 1.22
to get the distance to the horizon, neglecting refraction, this works.
Yeah,
and I'll show
like
you.
If it was a perfect world, that's what we would get, or whatever.
Yeah,
right?
So yeah, and the thing is, and this is what Austin and others miss, and I'll show you. I'm trying to find the presentation so you can see. There it is. Right there. I'll share this to you so you can see it here. Where'd you go? You disappeared.
Oh, I was just gonna play something for you in the background here.
Okay.
This is all I ever get from Craig or any of you
here
guys.
Is this? It might be a little small, but right here, this is Andrew Young's website. If you want to find it, you just search for Andrew Young distance to the horizon. This is it right here. The no refraction distance to the horizon.
Okay.
1.
Oh yeah, I think I remember you talking about this, saying that they were maybe using it in error. They were using it. They didn't continue on reading.
Yeah, they didn't read this part. They stopped reading before this. So yeah, so neglecting refraction. This is what you get: 1.23 times the square root of the eye height in feet. The thing is, this particular number comes from the radius of the Earth. Right here is the radius of the Earth.
Yeah.
And
it's a strictly geometry, is what you're saying. Strict
geometry, but here's the important.
It has nothing to do with reality necessarily.
The important thing about this is you don't get 1.22 or 1.23 from nothing. You get it from the radius of the Earth.
It's directly related to the radius.
It came from the radius of the Earth. That's where it came from. So when you're like, well, you need to do refraction on Austin and Q, where you're like, well, you can't use the radius of the Earth to calculate refraction. Well, if you can't use the radius of the Earth to calculate refraction, of course you can, then you can't use the radius of the Earth to get the 1.23 number. They both come from the radius of the Earth. When you're testing the hypothesis of the radius of the Earth, you use the radius of the Earth to test the hypothesis in all places where the radius of the Earth would be included. Okay. That's an aside.
So the 8 inches per mile squared, that works perfectly fine the way that I was describing it, doesn't it?
No.
Tell me where it doesn't.
Let me get back. So here it is.
Because I want to understand your mindset here.
So it's a 2-part thing. So you need to first, this is all without considering refraction. Mm-hmm. You first get the distance from the observer to the tangent point of the Earth, of the surface.
Mm-hmm.
Okay. Then you use 8 inches per mile squared to get the second step.
You're saying you can do it that way.
But it's only useful for the tangent point because
you're saying the 1.22 or the 8 inches per mile squared is only useful for the basically from the tangent point to the to the end of the line of sight.
So It's only, yeah, this particular formula is useful from this point to this point, and that's it. Not from here.
Okay.
You need to,
You
need
didn't
to
see my drawing, did you?
You need to get this, you need to get this distance figured out first to the tangent point.
There's another way to do it. I'm going to point at my thing again. You guys, hopefully you can see what I'm talking about. Do you see mine?
I do.
It very much looks the same as yours, right?
I will change it so people can see you.
And I'll try to just explain. I think there's two.
Oh, and I wasn't. Are you seeing what I'm drawing? You are. Okay.
Yeah, I was seeing what you're drawing.
Okay.
And maybe I'll just redraw. I'm just going to redraw this so you guys can kind of get what I'm saying. And I'm holding my camera, so forgive me for not being very good at it. Okay, so, and like you were saying, strictly geometry. We're not talking about refraction or anything like that. We have a circle. We have a center point to it. We have a radius, right?
Yep.
And so we could figure whatever number, but since the Earth is supposedly that size, if we use that radius, and plus our 20-foot observer height, so right here,
yep,
we have a straight line from the center of the Earth to the, we'll call it the camera or whatever. Now, forget about the rest of the circle. I want to go 90 degrees here. Okay.
Okay.
90 degrees. And we'll just pretend that there's a building here.
Yep.
It doesn't have to be, but we'll just say that. Now from our distance of the line of sight, however far we're looking, we go from that point down to the center of the Earth again. And you end up with 39, 59, and whatever.
Yep.
Rather than 20 feet, it's going to be a different number. And you can do this. You don't need a tangent point, because if you're looking 90 degrees, you're not going to have a tangent point, are you? Do you get what I'm saying? So you're drawing this and saying, okay, let me, what you're doing is you're drawing a line of sight like that, and you're taking this triangle and using your 8 inches per mile squared for this part.
Yep.
Or wherever this line of sight, and I didn't draw it very good, but oops, I'm sorry. Okay. But do you see what I'm saying? There's two different ways that you can do this. And your way is from the tangent to the center, right? And then to the distance from the tangent to the end of the line of sight down to the center. That's your right triangle. My right triangle that I'm doing is right here. And we're going to end up with the same numbers.
No, we will get different numbers. The problem is that you're not actually getting obstructed. You're getting drop. So it's just a different thing.
Drop. That's exactly what that formula is for.
It is for, you're right. It's for drop,
but it's not. It's actually Pythagorean theorem, right?
It is, but it's not. But it doesn't tell you the amount obstructed. It gives you the drop. They're different things.
But you can figure, like, there's other ways to figure it out. Like you were saying, you can use it from the line of sight. I'm just pointing out simply that when I did the math from a certain observer height down to the center of the Earth and the line of sight, and then down to the center of the Earth, I get the exact same numbers as 8 inches per mile squared, like within like the 10th decimal point being off or whatever.
Yeah.
It was almost exact.
If you use my formula here, this is what's used to predict hidden.
Yeah, so
that's what you need. If you want to do drop, your formula is perfect. It's accurate enough. If you want to do predicted hidden, this is the approximation.
You can still use the 8 inches per mile squared for that too.
As the second,
you just use it in a different way.
As the second part, yeah. But
use a right triangle, a different right triangle, right?
Yeah. Now here's what I use though, and I do it because the website I use.
I think it's funny that people in your chat too. That, like, I'm not even reading it. I don't even know what's going on in your chat right now. But when I go into, like, I think it's quite interesting when I go to your channel, because I have a wrench, and so people are like, "Stupid flat earther, you're an idiot," and they're just like telling me all these things of how I'm so dumb, and I'm like, I don't really think I'm dumb. I think I fully understand anything that I'm going to talk about. I'm not going to talk out my ass and say things that I have no idea about, because just so everyone knows, if you're on the internet and you say something and you make a video, there's plenty of people on
There's
the
gonna be
internet,
somebody who
including
doesn't
your
like it,
chat.
yeah.
Someone's gonna prove you wrong and tell you you're wrong. So if you're wrong, what I'm saying is you don't want to make a video where you're wrong. You don't want to be wrong.
Oh yeah.
Because it's easy to prove someone wrong if they're wrong. So what I'm saying is I'm not an idiot, and I actually, the people in your chat that call me an idiot are probably not even understanding what we're talking about right now. But
Ran out
whatever.
of space. There, I wrote the formula by hand. It's a tough one, but I can. It's much easier to just show it to somebody. I'll grab it.
See, I think this is the best kind of flat Earth debate or conversation that people can have, is one where they're actually looking at because right now I had no concept of what you just introduced to me with the right triangle being from the line of sight to, you know what I'm saying? That one. And I'm like, yeah, that would work just as well to find that what was hidden, the height of what or how much was hidden. But we can also get our drop from just putting the right triangle in a different place on that circle.
Yeah. All right. So here is, and this, I don't do that formula by hand. I just use this website here, and I'll show you.
Yeah, I do too. I just did it one time because I wanted to know without someone else telling me. You know what I mean?
It's Walter Bislin Advanced Curve Calculator. That's the best one out there. There is one that
GitHub
I liked.
has one too.
There's one I liked better. The GitHub one doesn't include refraction, and that's important.
It's just geometry. Just geometry.
Yeah, it's pure geometry. And but to do, you have to include refraction though.
You can't really do that consistently though, because there's days where
it varies, and that's exactly why. That's exactly why this is such a bad way to test the shape of the Earth. It is.
No, I agree.
It incredibly varies. So it
varies to my advantage, not yours. What I'm saying
I know, and that's dishonest.
No, it's not dishonest. That's what I'm saying is, if there's a lot of refraction, things are going to be lifted up or down or blocked or obscured. But if there's a day that's clear as a whistle, and let's just pretend that there was no refraction, that would be the actual measure. That would be the actual observation that you go with, and then you add refraction on the days where it's thick air.
There's always refraction. Right? There's always refraction, and when you're over water, it's worse.
Yes, but there are cases where there's less or more refraction. Yes. And if you just put a number on it, say add refraction, that's just garbage science to me. That's
you don't know the quantity, and so if you can't control for it, you can only guess. But here's the thing:
like you said, I agree. It's not the best way to find out whether something that's very hard to detect in the first place is there or not. You know.
Well, it's been measured, so we do have some quantifications of it. But here is you can't do this. You can't ignore refraction, because then Austin will get mad at you.
I'm claiming that you haven't even actually accounted for all the variables, and you're touting your trigonometry that literally hand waves dismiss one of the most important variables when it comes to perception, which is refraction.
I have to agree with Austin. Because what you're doing is you're saying, I looked across, Lake Michigan or whatever, and I couldn't see the city. So that's like what you're saying is that's what you're going to use your formula. You're going to say, oh, that was with refraction. But the days that you can see the city, that's much less refraction. Because you can see the city. That's what I'm getting at. There's days that you can't see it, and then the atmosphere is blocking it.
It's the opposite, but we'll get into that in a second. So here is number 4 is the formula that I wrote down. I wrote it in a line. This is stacked much more nicely. This website.
I'll give you a B- on that. I'm just kidding.
It's fine. This website, it actually derives how this was obtained.
Mm-hmm.
So,
this brings me back to like school.
this is what we did in school.
I don't even use any of this math. I'm a carpenter every day of my 44 years, and I never use any of this.
This is more math than you normally would need to do for carpentry.
Yes.
So here it is. We have somebody claiming to have worked at NASA, which is clearly a flat earther that. Claims to have worked at NASA is clearly a sarcastic account, but I would be glad.
Kind of like how I was on the ISS. Like I visit the ISS.
yeah,
Maybe
that
I'll have
was
to do that
sarcasm.
today. Maybe I'll have to go there today.
So anyway, so the point is, there's two formulas here, whether you have the line of sight distance between the observer and target, or the distance between them along the surface of the globe. So normally, when you have a distance of several miles, you don't have line of sight. You have latitude, longitude of the two spots, and then you know the distance between them. So the S is the correct number, and so 4 here is the correct formula. Right now, like Austin says, are you still there?
Yep, I'm still
Okay.
here. I'm just wardrobe change.
Like Austin says, you can't ignore refraction. So at high elevation over grass on an overcast day, 0.17 is a measured value. That is an approximation that you can use. When it's overcast and closer to the surface of water, 0.33 would be a closer approximation over the surface of water.
Okay.
If it's late in the day, and that's if it's overcast. If it's late in the day and it has been sunny, then you should go significantly more. The measurements of refraction over that particular surface are higher than 1.0.
Yeah.
But 1.0 is this only goes to like 0.999 because at 1.0 it's the top there. 1.0 is indefinitely far because the radius of the arc matches the radius of the Earth. So you can see indefinitely far.
I see. Yeah, like you'd see your own ass is what you're saying.
Yeah, if it were consistent and light.
Yeah, but that
far.
I've heard people say that. If the conditions were right, you could see your own butt from around the globe, which is just hilarious. But
and conditions could never be like that. So
I am doing interviews if anyone is interested.
The people only see you small for us. So just a second, I'll make it.
No, that's fine. That's fine. I just I've been up here for a while, and I frequent this station, and it's I actually have some information I'd like to share too about this station.
All right, let me
take your time, no rush, Michael.
It's all good. It's all good. Here we go. There it is. Everybody can see.
They can see me now?
Yeah.
I don't know if they can.
They can.
Really? Okay. So I just wanted to tell you, you know, the path of the ISS, like its trajectory.
Sure.
It's on the screen behind me. You see that?
Oh, yeah. Okay.
That screen's flat. Just saying. How's that?
Oh, that's awesome.
It is. It's a little stuffy up here, but they got great food.
Oh, I would I tell you, it would be tough drinking what you would have to be drinking.
Yeah, I don't know. That is probably one of the hardest things to like comprehend, I guess. Like I'm not saying I get it. I get what they're doing. They're taking any water out of what they're
recycling it.
And to me though, I just like what was it? Don Pettit said, today's coffee is tomorrow's coffee. I'm like, that's really weird to me. It's like, I don't think I could do that.
But I gotta say, most, maybe not you, but I think most flat earthers would be like, let's just not even filter it. I'm just good to go right back again.
I've heard about that too. Yeah, I've heard some of them.
Dave Murphy. Dave Murphy.
Yeah, I've heard people.
He'd be like, you guys filter your own. I'm good. I'm like
not into that kind of stuff.
Nope. Why would anybody?
Like, I don't even think my dog and cat and everything is into that kind of, like, no animals are really been into that kind of stuff. So anyway,
our dog used to, like, in the wintertime, used to go outside and find those poop sickles and
oh yeah, that's different though.
Why?
You know, dogs, they like that outdoorsy smell.
People, why do dogs do that?
No, I don't know. That's really weird. So the president, when Trump was president, he was talking to, what's her name? Peggy Whitson or whatever. Peggy, is that her name? Peggy Whitson. She's an astronaut. And she said, we're cleaning up our urine up here. And it's really not as bad as it sounds. And And Trump goes, what did he say? He goes, that's good for you. Something like that. Like, for you, not for me. I can't remember exactly what he said.
All right. So Mandevil says all the water we drink was urine at one point, just not as recently as on the ISS. And please, I just don't want to think about that. But
the luxury of going to space, you know, because like, let me just say this. Since space, like the planets like Mars or whatever, the places where we want to go explore, since they have nothing for a human being, like no food, no water, no way to live unless you're gonna like somehow take your supplies from the earth and bring them with you. What is the point of going to these places or trying to go to these places? Because you can't live there. You can have 3 people live on, or 10 people live on the space station for the resources of the whole world. You can do that, but it takes like a lot of money. Like a whole aerospace industry is like $400 billion a year or whatever.
Yep.
So that's quite the goal.
Yeah, it
doesn't make sense to me.
It's a lofty goal to colonize Mars, but I think
to me, unrealistic.
A critical part of it has to be that at some point you don't need to send resources there. You are self-sufficient.
Yeah, that's what Elon Musk says. It has to be sustainable on its own. Like you couldn't just send. This is exactly what he says. So you couldn't just send a few people. It would have to be it would have to be, whereas if the ships stopped coming from the Earth, that they'd be able to do their own thing. Like yes. if the transportation ability or capability disappeared somehow, that they'd be able to maintain their civilization. But I do got to run this by you too, and think about this once. And I'm not going to make a big thing out of it, but I will mention it. Okay. When was the last time that we in this world had someone that was claiming to create or whatever you want to call it, a world for people to live on? Just think about that, because I think that there's biblical stories.
What the hell even is that?
What
the hell even is that?
What do you mean?
What are you talking about?
Like trying to be like God. I'm just saying, like, we can make our own planet and move there and live there or whatever. Like God, I think God made the world, and it seems like that's in the Bible, that towards the end, where there's going to be a man that kind of says that he can do those things. Anyway,
okay.
I didn't want to make a thing out of it because I am enjoying our discussion. Okay. I don't want to ruin it.
All right, so here is, and people were asking this. So what is the flat Earth prediction for obstructed? How can we test the hypothesis for flat Earth?
Oh, you mean like how the bottoms of stuff will disappear? Like,
yeah, because I've got the formula. I showed you the website. We talked a lot about the math for how that's done on the globe, but how is it done? How do we predict the amount hidden on flat Earth?
I don't know. That's a good question. I think it'd be very much similar to how we predict it, but obviously a different way. But I'm saying the numbers would be very similar, or the amount, I should say, would be very similar, because
the results are similar. They would have to be.
That's what I mean. That's what I mean.
But I've never seen anyone
come up. No, I haven't either. I'm not claiming to have that knowledge or idea even.
So let me go over it then, because I think it's worth it.
My head is kind of, as I watch, my head kind of starts falling off to the side.
I have to keep
myself straight.
All right, here is.
Wait a minute. It's actually more fun if I have a bigger head. It looks way cooler.
It does. Yep.
That's way better, isn't it?
Okay.
All right, what I'm going to do is, since I just ruined the whole secret, that's Alexander Gerst. He took a sweet time lapse of the Russian Soyuz launch.
Okay. Okay, so here is the flat Earth hypothesis.
Yep.
So there is something obstructed somehow.
Or
Because
maybe not obstructed, but it's
you can't see it.
obscured. Maybe I don't know the right word.
And
You can't
so
see it. It's like reflected or something. Yeah.
And
I know what you're saying.
There's two very important things. Increasing the elevation reduces the amount that's obstructed, number one. Number two, increasing your distance increases the amount obstructed. So whatever hypothesis, it needs to include the elevation and the distance.
Well, and I think I might have a little bit different of wording for that, the way I understand it. Like what you're saying about the elevation of, like if you climb a ladder, you're going to see less obscured, right?
Yep.
And the way I'm thinking about that in my mind, like I agree with that. So if you climb that ladder, what you're going to be doing is when you're looking at the same thing, you're going to be looking at it from a different angle. So like if you were looking at, like if you're in Hollywood and you're looking at on a ladder at the Hollywood stars on the sidewalk, where you're going to be able to read them better from the ladder, because the angle that you're looking them at is closer to a 90-degree angle that you'd look at something at than a reflection where, you know what I'm saying?
I do, but it doesn't give a plausible explanation for what's going on.
I'm not claiming to have a plausible explanation.
Well, and that's the problem, because there are definitely something obstructing it. But if there isn't a plausible explanation for it, then you don't get very far.
Could we word it like, would it be accurate for me to, instead of saying obstruction, to say like, what's the word I'm looking for? It doesn't matter what word you use. You can't see the bottom of an object, and it gets more of it you can't see when you get farther. Yep. And I think that's part of how our eyes work, part of how we see everything.
Well, cameras miss it too.
Same thing with a camera.
And the amount of zoom doesn't change it either.
No, I agree. It's something that it's like, when I'm just thinking of like a situation where I look across Mille Lacs, okay, and I see, like, I was there a calm morning and I had my camera at one of the landings and I put it right down on the water because there was no waves. There were almost no waves.
Yeah.
And from about if I'm being precise, is about a 3-inch or 4-inch viewer height for my center of my camera, because I actually got my camera wet. I could look across the lake and I can see all the trees on the shore on the other side. And I know that they're on the shore because there's a water tower that's a 1/4 mile away from the edge. Actually, the water tower that you sent me a picture of, name it, that one's a 1/4 mile from the shore, isn't it?
Probably.
It's up on a hill a little bit.
Yeah.
That water tower, there's trees between that water tower and the other side of the lake that I could see. And so I know they're either they're in that 1/4 mile is what I'm saying. So they're basically right on the shore or on the other side of the road or whatever. And I forgot where I was going with that. Oh, I can't see the bottom of the trees. It's just too far away to see that now. Yeah. And then if it's windy, you're not even going to see those trees. Yeah. If it's windy, you're not going to see the trees because the water lifts up.
It's non-optimal.
Yeah. But I know what you're saying, though. You're saying, why is it obscured? We need a formula or something is what you want.
Yeah, you do. People talk about that it's something to do with the angle, right?
Yeah,
when the angle here gets to be something.
Yeah.
But the problem is that, and here I'll draw an angle.
Straight across and it's not obscured. Yeah.
No, it's actually, it's this angle here. So when we match this angle,
there's not ground between you and the top, though.
But there's no ground between you and the bottom, so there's nothing in the way.
No,
so
but there actually is.
I'm going to try to make the same.
There is ground. Yeah, I see what you're saying. There is ground beneath both observations, but the one that's going right along the ground, when you're driving on the freeway, and you'll know exactly what I'm talking about, and you're going to call it a mirage or whatever. You're going to call it like refraction, I guess. When you're looking at a car that's a mile away from you and their headlights are bouncing off of the road, you get that reflection of their headlights.
But But that doesn't obstruct the headlights. You still see the
No,
headlights.
but
Okay,
it certainly does.
So
It
so
certainly
here,
does obstruct the headlights. What are you talking about? If it's 2 miles away, those headlights are like one headlight. Like you're not, it's
yeah, because you don't have the rest. You can't resolve the difference between them. But here's the angle, right? You've got the same angle here and here.
yeah.
If
Yep.
if for some reason some part of the bottom of this is obstructed,
The top should be, you're saying. And I
then
disagree
this
with
should
that.
be obstructed too, because
You're not looking along the
there's
surface
nothing-
of something.
but that doesn't block.
It does.
This
It does.
This here doesn't block this line of sight.
I'm gonna try. No, but you're obviously, for one, you're drawing it on paper with a, that's about a 15-degree angle or whatever. And when you're actually looking, it's like 0.0001
it's
degree
a
angle.
small
You know what
angle.
I'm saying?
It's a
Very
small
small
angle, yeah.
angle. And that's
This
actually
is-
why one of
it's
the
not-
things I wanted to
it's
talk about.
Not to scale, right? But that's
Like if we're looking at the sunset and if it's a flat earth and then the sun's going away from us, that sun is
but we're
not going to
but
stay
Let's
up
not talk
in
about
it.
the sun yet. We're
Okay,
talking
but-
about a building here.
But a concept though, I shouldn't have said sun. I'm just saying something at a distance, it's going to eventually disappear into the horizon, even on a flat surface. You can't see it forever.
Yeah, because it's this angle
Yep.
is going to be too small.
Let me
resolve the
understand what you're
details.
saying. Well, and I'm not necessarily
Right.
talking about resolving. What I'm saying is, as the airplane is flying away from you above your head, same as the bowling ball leaving your hand going towards the pins, but just upside down.
Yeah, this
it goes-
angular size
if you
shrinks.
look at it,
The angular size
you look-
shrinks as it gets farther away. That's
as it
perspective.
gets farther away, and your angle gets closer to zero as it's farther away. And no matter how, and it continues on that way. I'm not saying it's ever going to get to zero, but it's going to be
Yeah.
nearing
So-
zero. So it's going to
yeah.
go down into the
So
ground. It's going to
at
appear
some point, this gets too small to resolve.
yes. Yeah.
That's it. But when it's not too small to resolve, that's what we're talking about. When this is
Yep.
this is the deal. And there's nothing between here and here.
Well, there is, though.
But for some reason, a chunk of it is not visible. So why is
It's-
this particular part?
Because you're looking almost nearly exactly parallel with the surface. No matter,
but what
even
is-
if you have a 25
but what
foot
is
height,
making that part of it
ground.
not be seen? But the ground's not in the way.
the ground is in the way.
No, it's
I'm not saying
because
no,
there's a
this is
straight
why I'm
line of
saying
there's an
geometry. No, this is why I'm saying
unobstructed line of
geometry
sight.
doesn't work to portray reality in this way that you're saying.
but
That's
what-
my take on it.
What is the plausible mechanism that causes you to not see the bottom?
The same thing that happens when you get a reflection from headlights on a car that's coming at you a mile away. You get a reflection on the road, but is there light actually?
So
do
you're
you know
saying
what I'm
that we
saying?
should see more of the building?
No.
Because
You're
if you see a reflection of the light on the road, you're seeing
Yes.
more of the light.
You're seeing a reflection
yeah,
of
but you're
that
not.
light.
But unless the surface of the water is super flat, super not wavy, there's no
And, yeah.
there's
No, if it was perfectly mirror water, you wouldn't have anything between you and what you're trying to look at. So the
Yeah.
bottom, you would think that the bottom wouldn't be obscured. And I'm not saying that I have the answer to this, but there's something that needs to be considered if we're being honest and talking about this. And what I'm saying is when something's going away from you, I don't care what it is, and we can use the bowling ball is a good one. If you're at a bowling alley, you look at the ball in your hand before you throw it. You're looking straight down at the ground. You're looking at the ground at 90 degrees or whatever, right?
you're,
and then
all
now
you're,
you
you're
throw
just
the ball.
describing angular size. That's
No,
fine.
it's not angular size I'm describing. I'm talking about the horizon and the bowling ball. Like it's just the opposite of the sky. It's upside down from the sky, but the bowling ball, it actually works good because of the size of a bowling ball and its angular size. But as you throw the ball, if you're watching the ball, which direction is the ball going? It's going for your apparent, like you're apparent to you, it's going upward toward the horizon, toward the bowling pins, right? And if the bowling pins weren't there and it was a flat surface and that ball just kept rolling, like you're saying, it's an angular size thing. It's going to disappear like that. But if we had the equipment to watch it, what I'm saying is eventually it's not going to be able, like, even if you're
it's just a hypothesis though.
well, yeah, I'm just saying that there's I took my camera one time. I wish I had the video. I might be able to
hold on.
Okay.
You I asked for the plausible mechanism and you don't have it, and that's honest to say you don't have
can't say that I have a plausible mechanism that would come out in a formula, but I can tell you that a lot of the things that I observe in this world go right along with that. And like you're saying, the angle that's going toward the top of the building, that's not nearly as close as the one that's looking at the bottom of the building.
Well, if the building's high enough and
I'm saying
and you are not right, if it's a 100-foot building and you're only 20 feet high,
yeah, then you're going to it's going to be obscured at the bottom more than it is at the top.
And say the bottom 10 feet is you can't see.
Yeah.
Right. Then
where's the thickest air? The most dense air? Where's the most dense air?
Yeah.
Below your 20 feet eyes or above your 20 feet eyes?
But you don't see blur.
I'm not
in
talking
these
about
examples
blur.
because
I'm talking about literally being blocked by the atmosphere.
Okay. But that's not what you see. You see water and you see building. Where is the air blocking it? The air at no part.
I can show you with the sun.
Hold on. I'm not talking about the sun. We're talking.
No, I know, but I can show you what you're talking about.
But
that
at no point do you not see the water or the building. If it's just air blocking it, then you would see neither water nor building where the air is blocking it. I
don't think so.
You'd see
blur.
blur.
If you're looking at long distance. You're looking right along a surface. Right?
You'd just see a blur. That's what the air would. If the air is obstructing it because it's so thick, then you would not see water. You would not see building. You'd see just the air. Let
me show you. This will give you maybe an idea of what's going on in my mind here. I have a video of the sunset setting, like not setting, but it appears. Let me get it up on the screen here, and I'll move out of the way. The sun, let me, sorry, I'm just playing the video. I'm trying to get over to my,
yeah.
I'm just going to skip ahead to, okay. So this is from 1,500 feet in the air, and I'll zoom in, don't worry. I did a few different ones, and okay, here we go. Now I know it's blurry, but you'll get the idea. The sun appears to be setting up in the air almost. You'll see in a minute. And it's getting dark from the bottom side up. And that's clearly like this right here. You can see that it's clearly because of the thick air that's below the drone.
You mean clouds?
Well, there's no clouds. I could see the ground perfectly fine. It was just thick air. Okay. So you see how it did get dark from the bottom side and it went up. Do you know what I'm saying? So that could either be the sun going kind of down through it as we're looking, or it could be from, you know what I'm saying, right?
I know what you're trying to say.
Yeah. So what I'm getting that same idea is that when we're looking through that thicker layer that made the bottom of the sun dark, we're going to get much more things blocked than if we're looking at the top of the building, aren't we? Here's maybe a better video of it.
Yeah. So you were seeing not ground and not sun.
Well, you can see the sun still, but here, I'll zoom in. You can see it still, but it's just getting dark. You know what I mean? It's because there's obviously air or something in the way, but I can see these lakes down here and everything just fine. It's just thick air. There's clouds above. This video, if you want to watch it, I do have it on my channel in 2160p, and it's much better to watch in that. And I can't remember what it's called.
Is that your video you said?
Yeah, that's my video. And
that's over Mille Lacs?
No, that's just above my house. That's just
okay.
land I'm looking over.
Okay.
Oh, look at that flat. Let's see here.
All right. let me read a couple things here if you don't mind. The Sun Express is effed up. One observer's sunset is another observer's solar noon. What's the altitude of the sun right before it reaches the horizon?
I don't think the sun has an altitude. I don't think it's in a physical place in the sky as we perceive, like the space station would be 250 miles up. I don't think the sun is at all like that.
So what is it then?
It's celestial. It's part of the heavenly realm. It is a.
So
I guess
your answer is just a question mark.
No, my answer is that you would make a positive claim that the sun is a certain distance, or that it's a certain size, or that it's a certain temperature, whatever. You're going to make a claim, or not necessarily you, Toon. I'm just saying.
Oh, I will. Absolutely, I will. Yeah.
Yeah. So you'd make that claim, and I just simply wouldn't make that claim. That's all that's happening. I would say, I don't know.
Okay.
I don't think it's a certain height because it doesn't work out.
Do well.
It does just
flat
fine.
Earth, right? It
does just fine because
it's at least honest. But
I would rather be honest than make something up.
I definitely appreciate that, and that puts you above a lot of other people that I've talked to.
Well, and I see, like, there's a lot of people, like, I guess it's kind of unfair to, and I guess we'd call it straw man or stereotyping or whatever, because I get that all the time in my comments on YouTube. I get it every day, actually. Oh, well, that didn't seem to work out for you to, like, whatever. And they just straw man something, and I'm like, they're like, yeah, because that I don't believe that they're faking space. Nobody's faking space. There's no conspiracy to fake space or to pull. Nobody's hiding the shape of the earth in our government or something. That I don't think it's on that level at all. I don't think there's a conspiracy, and it would be impossible for there to be one. And so then, well, do you believe in the moon landing then? I believe that they went to the moon and they experienced what they experienced. And like you were saying, your buddy Charlie Duke that you met, I don't think he's lying to you.
I don't think
he experienced what he experienced.
But he's a little too,
well, you met him. I just say that to kind of tease you.
I have a picture with him, and he signed a book that I have.
You went to lunch with him, so that's more than most of us have done, right?
Yeah.
As far as meeting Apollo astronauts.
Okay, so the thing is, the problem is that we have bounced radar off of the sun. So
yeah, even before we went to the moon, right? Radar off the sun, and you think that that's something that you can do? And yeah, look at that, we just bounced a radar off the sun. It's 93 million miles per hour. Are you kidding me?
What?
You don't know. It's not even tangible.
Why is? But that's that. I mean, that's just a claim. It's not even tangible.
The heat from the sun is tangible. You can't touch it.
Okay,
you can't go there. Right?
Okay, what is your explanation for the ability to bounce light off or bounce radar off of the sun?
You don't know what you're bouncing radar off of. Like, you're pointing a radar up at the sky and you're receiving a signal, 16 seconds later?
Almost 100 seconds.
Almost 100 seconds.
Yeah.
So, and that means that something's bouncing off of the plasma or fire or whatever that the sun is made of.
Yeah.
So let's do that on Earth. Can we bounce some radar signal off of plasma?
Yeah.
I don't think we can. Because plasma is an interesting thing that you can't even send a radio signal through plasma. Like when they're re-entering the Earth's atmosphere in the shuttle, or there's this blackout.
Thin layer of plasma. Yeah.
Yeah. And so actually that's an interesting thing that you might understand and give me an answer where I have no idea. And it's interesting to me. How does that, what is the properties, or what is the properties of plasma that it won't let radar, or I guess not radar. I don't know what kind of communications they're using, but whatever communications they're trying to use, radio or whatever, it won't penetrate through that plasma. And so for the 9 minutes when they're in the shuttle, or the 3 minutes when they're in Apollo or whatever, that they're coming in, that there's a complete blackout and there's no communications. That's weird to me.
It is. And we can maybe discuss that.
So how do they bounce radar off the sun?
So there's two different papers I have listed here on my website at mc2.net/sun.
Oh, this looks like the good old days.
And this is from
1966.
Nice. Look at that. I don't think they'd get away with it today because it's a super strong radar signal, and it would definitely be too strong for any
satellites
legal,
or something.
For any legal human exposure.
Oh, okay. Like radioactivity or whatever, isotopes or something like that.
Yeah.
Is
did
that
I say? All right. How much time did I say it took to bounce?
I think you said 100 seconds.
1,000 seconds.
Okay. Okay. 1,000 seconds.
Which is 16 minutes.
So it's moving way slower than the speed of light.
No, it's actually moving at the speed of light.
Okay. So the speed of light, you know what? 8 minutes, not 8 seconds. 8 minutes is what I was thinking. Okay. Yeah. I'm sorry.
Yeah. 1,000 seconds.
16 minutes would be your round trip.
Yeah. Which is about 1,000 seconds.
1,000 seconds. I got you now.
So, yeah.
I was on the.
So here is. So there's a couple of these, and then
whoa, I saw plasma. Can you go back up?
Just a second. I'm looking to see. Oh, I didn't add them yet.
I saw plasma bouncing off, something like that. I want to see.
Oh, there it is. I did add it. Okay.
Plasma theory of solar radar echoes. I want to hear about that.
So
Tell me about that.
Radar scattering by the ion sound turbulence accompanied by type 3 Langmuir turbulence is considered. It showed that such scattering explains reflections from heights greater than 1.6 R0 observed by James, 1966-1970.
Okay, what does R0 mean? What does that mean? Greater than?
It's
or
being
less than.
Being that it's a quote. I don't have this, so that would be
okay.
I think it's a radius.
Okay, something. It's some
value,
like
value of radius from the sun.
It's like an abbreviation for
this.
A value.
This was published in 2003. So there's legitimately questions about can you actually bounce radar, which is photons, off of plasma, which is ionized gas, which is protons and neutrons in mostly helium and hydrogen.
You have
atoms.
a direct PDF download to that. I'm gonna have to look that up. Where is this that you're looking? Mictune.net
/sun. Yep.
Okay, I'm gonna have to look at that.
So there you go. And I think the second one here, this is another one.
Because that's actually I made a video on my channel asking anyone that watches the video. I want to understand the more about plasma, and I want to understand mainly I want to understand why their communication is lost during that re-entry. And they say it's because the plasma they go in like a plasma ball forms around the vehicle because of the heat and pressure that it's coming against, and that their radio signal doesn't penetrate through that. And to me, I'm like, I don't understand why that would happen, but it's something I've wondered.
You can, for example, block radar and radio communication with
plasma,
with a grounded conductor.
Okay.
So,
but a conductor that's not a plasma.
So so like when people actually do shield their houses with tinfoil, it has to be grounded to be really effective.
Kind of like my tinfoil hat.
It's called a. Where's your tinfoil? I want to see your tinfoil hat.
It says Flat Earth Doctrine on it. What are you talking about?
Oh, that one.
I'm just kidding.
It's a.
I'm not even on the screen.
It's a Faraday cage.
Yeah, a Faraday cage. Yeah.
So all right, there you go.
So
all right, so let me. I gotta read a couple of these here because we only got to one.
Go for it. And then I have one more thing to bring up if we have time.
Okay.
One more kind of like thing I was thinking about. So anyway.
I like to keep it around 2 hours. Otherwise, people are like 3 hours. I can't watch that whole thing. Anyway, Alyssum says, "Effed up. I have a question. I want you to answer honestly."
Got it. I will.
Why is all navigation based on a globe?
It's not. You know how navigation is done? It isn't something that's done today in one day. It's actually something that has been since the beginning of time. Men have traveled and they've navigated all over the earth, and they've drawn maps, and they've formed an idea that there's a sphere, but the maps don't have to be on a sphere. You can still get from point A to point B and draw a map of it that's not spherical. So it's not based. Navigation is not based. You're
do
talking
you
about like
have-
maybe flight navigation or
Do you
something. What are you talking
have
about?
such a map that is strictly flat and doesn't include any projections?
No, I don't.
That
I don't.
works?
I don't claim to have a map, but I claim
Okay.
that if I went to your house, Tune, and I took the highway up to my house, I could draw you a map that would be accurate. I could even do it to scale for distance and everything. It wouldn't have to be curved in order for you to get to my house from my map. Right? You get what I'm saying?
I get what you're
A
trying
map
to
is
say.
not a globe. A map is not a globe for the reason of navigation. Navigation, I mean, maybe I said that wrong. Navigating on the Earth does not say anything about a globe or flat. It's just navigating on the Earth, just like it's always been. The ideas we have of
All
a
right.
globe have come from years of making
Trial and error and
yes.
fixing the errors. So let me explain
trying to.
important part of it.
Okay.
When you load the fuel onto a plane, you need to know
Yes.
how much fuel you need for that trip.
Simple, yeah.
If you load in not enough fuel, what happens?
You won't make your destination.
That's a bad thing. If you load too much fuel, what happens? In a large
you
in
have
a large
the
airplane.
capability to go farther, slower.
But in a large airplane, what happens?
You are gonna go slow, or you're not gonna take off, or whatever. I don't know what you're trying to say.
Well, if it's still within the ability of the plane to take off,
Then
what's
you'll go
going to
slower,
happen?
I suppose, and you're not gonna
You
get
could-
the efficiency.
It hurts the efficiency, so that
Yeah.
the airlines want maximum efficiency to maximize profits.
Hmm.
But the big thing is, an airplane has a takeoff weight and a landing weight, and they're
Yes.
different.
Yeah.
So you cannot take off a large jet and then loop around and land unless you dump fuel.
You're just saying because of it's not safe to land with too much weight of fuel.
It's got too much
So
weight.
you're just saying all you're trying to say is that they only put as much fuel as they need for every flight.
Plus spare. They have terms
Enough,
for it.
yeah,
but
just enough to be safe.
So if they used the wrong formula, say a formula that gave them too long of a distance between points, they would always load up too much fuel, and they would always get to their destination and say, "Oh crap, we can't land. We need to dump fuel." That's
This is not a good.
It's a very wasteful way to run a
this
business.
is not a good. This is not a good. This use of time if you're trying to prove something about navigation on a globe, because if you look at the navigation on a globe, you're apparently not flying your plane in a straight line. You're flying in that great circle.
Yep.
And so what I'm saying is flying in that great circle. I don't know. A lot of people, there's this other flat earth map, whatever they call it. I don't even know what they call it. The flat earth, the one with the ice wall.
Yeah.
That's obviously got big issues all over the place. But that idea, it does seem that
right.
There's other ways to look at the. I don't think navigation is based on a globe. That's basically my answer. Sorry.
All right. Well, let me finish the idea. This particular map,
which is wrong, yeah.
Which is definitely wrong.
Yeah.
You can't use the same formula to calculate distances on this map.
I don't think you would want to.
The formula.
I don't think the distances are accurate on that map. So I don't know why we would try to.
So the distances that they actually use is the Haversine formula, which is a spherical trigonometry formula.
Mm-hmm. But that, yeah.
So
to me, that's like.
But if the surface of the Earth is flat, then that formula is going to give you the wrong numbers, and you would need to use.
No. On your false map, it would. But if the surface of the Earth is flat, those numbers work because it's the Earth and we fly over it all the time.
But
it has nothing to do with the map.
But it does.
What I'm saying is, if you fly if you fly from LA to Hawaii, it's a certain distance.
Yeah.
And you're saying
how
it's
can
a
you
different
calculate
distance?
Yeah.
You're saying it's a different distance than it is, or what?
Different
Because
geometries will give you different distances. If
you use a fake map.
if
but-
the surface,
but we're not- I'm not
let me
concerned about
finish
a
my
fake
thought.
map.
Let me you keep
Okay,
jumping
sorry.
in. You keep jumping in.
I know.
If the surface of the Earth is a sphere, then one formula will give you an accurate number.
Yep.
If the surface of the Earth is flat, then a different formula will give you a different number. And the longer the flight, the farther you will deviate from the
because
correct amount.
There's no accurate flat portrayal of the Earth in map form.
Yeah.
What I'm saying is the thing on the screen right now on your desk, that is I call it a flat Earth map. I mean, I think everybody kind of
Hold on,
everybody kind of sees that as
I'm sending you the
flat Earth
wrong.
map.
I'm sending you the wrong picture. Hold on.
Oh, okay.
I thought you were seeing my face instead of my desk.
Oh, okay. No, I was looking.
Everybody
at
everybody else is seeing. So,
okay,
all right, there
you know
you go.
that flat map though. That's I think it opens up ideas or concepts, but it's not at all accurate.
So I totally agree. But on a flat surface, you need to use a different formula than the Haversine formula. So, all right.
Okay.
Bernie Bierman says SS motorcycle racing. Look it up. Explained with buoyancy and density. Go.
Nah, I don't know. That's boring.
What?
When someone says go, I don't really go. I do kind of tend to do the opposite.
What does
tend to stuck my foot and say, "What'd you say?"
I don't know what SS motorcycle. I'm Googling it. I don't get any.
Apparently it's I'm guessing it's like a motorcycle race maybe that they do. Maybe it's a long track or something.
But I don't know why buoyancy and density would mean. All right.
Go.
Cretan Ball says, Joe, you are too smart for flat Earth. Come back to reality.
Hey, you know what? I'm trying to wake you guys up. There's another way to look at the Earth. There is. And Michael Toon, I know you can understand that I'm not an idiot, and I am. There are some points that I'm making.
That's why I'm with Cretan Ball so much.
And that's fine. That's fine. I know we disagree on things, but I do like if I had a desire in these conversations or debates or just, friendship or whatever, it would be that not necessarily to make you a flat earther, but it would be to maybe bring my beliefs that I believe to maybe more of a reasonably understandable position than I see most other flat earthers doing.
So let me ask you this then.
Yes.
What would it take? What would convince you that the Earth was not flat?
The Earth is flat. So nothing.
What would? Okay, so you don't
if there was if I went to space, hear me out. If I went to space and I got to see what Charlie Duke got to see, with what I know now and what I believe now, I would say, hey, that looks like a globe, but it's not a globe. Do you understand what I'm saying? My eyes might see a globe from space, but I think that what eyes in space see are not at all accurate.
So you could not be convinced by anything.
The ISS, the astronaut, I was just showing you Alexander Gerst, from ESA. He's up on not now, but he was up on the ISS and he's taking time lapses of things and everything. I believe that that's all just straight up legit footage, and it appears to be spherical.
Okay.
But it down on the ground here, it's not. It is not spherical.
There is no evidence that would convince you otherwise.
Because of the place that, and I'm being honest with you, Toon, the place where I started to believe a different thing than I believe. I'm 44 and it was like 37 or 38 years old. Something changed in my mind or in my heart or whatever you want to call it. And I didn't do the change. And I'm just being straight up honest with you. I didn't do the change. I started seeing a different world that I never considered, never comprehended, never thought about my entire life. And when I started to see it, here I am for all these years with trying to talk about it because it's such a huge change in my life. It changed my life. So that I'm just being honest. So yes, nothing would convince me because I learned it from what I consider to be the God of creation. And I'm not saying he came and spoke to me and, hey, Joe, guess what? What I'm saying is the other ways. So
I'll move on.
Yep.
Andrew Stoll says, MC Toon, let him show us his math. And that was where I tried to get you to show us the math for how much was obstructed.
Sort of did.
And no, you don't.
Well, I might have not used your way of that Pythagorean theorem, but I used a different way that works just as accurately. It gives it the same number. So a right triangle.
The drop.
But it doesn't,
right.
the drop, but it doesn't give, I don't know how to figure that. So
all right. So the logical hillbilly says, Joe thinks Toon is the confused one here. Who's talking about the Pythagorean theorem stuff. And then,
well, I think we were actually talking about two different things right there, because I was talking about a line of sight being tangent. So I was maybe being confusing.
Yep. Tribal Guy 2 says, Joe, your problem is that all your efforts amount to futile endeavor to reject everything that disproves your predetermined conclusions.
Yep. Thank you.
Glad you accept
my
that, I guess.
My predetermined conclusions were the ones that I had for the first 37 years of my life. And then the other ones that I have now that differ from that are not the predetermined ones. They're the ones that I came to the conclusion of after I after I bought a bunch of cameras and went out and did a bunch of studying and researching and whatever. I'm not saying I can do all that right or that I know everything, but I'm saying what I have learned is that I look at it differently, and there is a legitimate way to look at it differently. Man, I'm pissing you off right now, aren't I?
I'm not mad.
I know.
You
love me.
I'm sad. John Rapp says, NASA advises alert, Poe detected alert. I don't think he's a Poe for 1 second.
I'm just being straight up, and people call me a liar all the time, and I don't care.
I think Joe is the opposite of a Poe.
Joe's a schmo. They call me Joe the schmo, or they call me Joe Mama sometimes. But
so Heat Shield is wondering, he said, eyes don't see the same in space. Why?
Because you really want me to explain what I think here? I can do it quick. What is space? It's a universe or a heliocentric solar system, they say, right? Or that's what the world, that's what the science would say, right? It's a solar system. It's a void of air. It's basically void of everything except for like planets and whatever we can see, stars, whatever. And it's dark. It's a place of darkness. Now, this is interesting.
It's actually quite bright if you're near the sun.
There's no shade from the sunlight. That's
there's no
sunlight,
shade.
though.
Yeah, there's no shade from the sun. You can't get
No, but
away
if you
from
go
it.
above the earth, you're in the atmosphere of the earth where it's like a blue sky and everything. But once you get up above that Kármán line, it's darkness. That's what it is. It's darkness. Okay. Even the astronauts. Now, Toon, you might not have thought about this before, but everything in space that's staying in space, everything that's in space right now, like anything that's there is falling perpetually around a larger body or another thing. So it's free falling.
Yeah.
It's a state of free fall. So everything that is in space is falling. Like the space station, for example, they threw it up there and it's been free falling perpetually for 22 or 23 years, and it still hasn't got to the bottom. It's a bottomless pit of darkness. Just think about that. It is. And my understanding is angels or whatever. I know it's not a big topic for your crowd or whatever, but I'm just sharing what I believe, and I'm trying to do it briefly so I don't bore everyone. I believe that there's a such thing as called spirits, and there's good spirits or angels, whatever you want to call them. There's bad ones, and there is a place of imprisonment in a place of a bottomless pit of darkness where there are several deceiving spirits. And I think they lure men into that darkness and deceive them. And they do it. It's beyond like a trick. It's more than that. It's on a different level. So
why couldn't space just be space?
It is.
Why couldn't it just be?
There's a specific. You can't go there without moving. You have to do this very specific thing in order to go there.
So,
And it's not just getting in a rocket. You have to go specifically parallel with the surface of the Earth at orbital velocity in order to even go there. Otherwise, you're not even there. You can go straight up with a rocket, you're going to come right back down.
But that doesn't mean that it can't just be space.
It is just space, but it's a place of darkness. And I just remember Jesus casting unclean spirits into outer darkness. I think that's where they went. That's just my take. And I'm not trying to push it off on anyone, but you asked. So,
okay.
But actually I am, because I talk about it all the time on my channel. So I'm trying to tell people about it.
All right. Well,
is that it? Is it all over? You know what? I do want to have another conversation with you sometime in the future.
Yeah.
About your picture of the curvature that you were just showing to that poor guy in the last stream. I got there's some serious flaws in the logic that you're going about there, and we could do that next time. How about that?
Sure.
We can talk about it at some time. Anyway, maybe in private messaging.
All right. Hold on a second.
I think he's got to go, you guys.
All right. That's was my wife. She's tired. Going to bed soon.
Me too.
I have to get up in the morning to drive to work, which is right
Me too.
here.
I wish I could say that. I wish I could. I'll be driving right by your house tomorrow. We could get lunch one of these days. I can't believe we haven't it's been like a month and a half that we were talking about doing it. And then
you said you were like super busy. Is that kind of wrapping down a little?
Busy, that. I haven't even been on YouTube very much. Like if you look at my channel, I put a few videos up, but usually I put way more up. I've just been super busy.
That's probably for the best. It's okay. You don't need to.
It ain't for the best, but yeah, I'm just kidding. Someday, like today, I was around here, but
is it the time of year because people are trying to get stuff before
it's just
winter?
I have a hard time saying no to people. I'm self-employed and I just do whatever I feel like doing, and people call me all the time, and I get to kind of pick what I want to do. And so sometimes when I pick the wrong one, I'm like, dang it, I should have done the other one. But I end up working a lot more than I would like to sometimes.
All right. Well, tomorrow, so my kid, I have several kids. 33 is the number I give people. It's clearly satire.
Isn't there someone that comes to your channel that gets timed out? Name that. I think. Anyway,
33. Yeah. No. So I am not very good with vehicles until I had my one kid. So he's really good with vehicles, and I taught him everything I know about vehicles. It took 5 minutes. Then he taught me a lot about
all the
vehicles.
Rest, right? All the other stuff.
And he's I can't. He did not get it from me.
Is he is he like grown up, or I'm not trying to pry. I'm just
kidding. He's an adult, and
he's telling you how it is with the car.
Oh yeah, when I have trouble,
that's cool.
I call him. So.
But that's cool for you to be able to say that, I think.
On Friday.
Yeah, my son tells me about this stuff I know anything about.
On Friday, another one of my kids was driving his car and the car died. We had to get it towed here. So then today, son that knows about cars was able to come over and look at it. They got it working, of course.
No way. Nice.
But, yeah, it stalled on the side of the road. It was the mass airflow sensor.
Oh, wow.
So, but here's the deal. The one who owns the car that stopped
So does that have like a blower then, or a turbo?
No, it's just a sensor inside of it. And so the one that needed help, he's not good. He has other things he's super good at. So the funny thing is, they had to pull it, our driveway, there's a hill to our driveway. You have to pull it up. We could not push it up the driveway. We had to get it out of the street. And so he used a tow strap to pull it up. Well, the younger one didn't quite realize that you need to hit the brakes when you have a slack tow strap. So on the passenger front quarter panel, he hit my other son's pickup, And so tomorrow, midday, I'm driving up to Upul, I think, which is on
No
Central.
way.
Yeah.
That's by my house. I'm not even kidding.
Yeah. So
And I'm going to be an
driving-
hour and a half south of there.
I'm driving way the crap up
You
there.
pull it. It's called. You pull it.
Yep. To go and get a right front quarter panel for this vehicle.
Let me guess. That's in East Bethel, right?
Yes.
East Bethel?
Yes.
Okay. Got it. I've been there. Hopefully you can find what you need. It's kind of a crazy place there.
My son already called, found out, verified that they have the vehicle there.
That's
So,
awesome. That sounds like you got quite the cool family going on. I think that's awesome. Like, I already know that you homeschool and you have some younger ones that you homeschool. I just think that to get like your son that teaches you how to work on cars, like that kind of thing doesn't come without somebody pushing them in the right direction. So good on you.
Well, thanks. But yes, we definitely need to get that. Anyway, that's a different thing.
Thanks,
So
Tune.
thank you, Joe. Thank you to everybody watching along. I hope it was worth the watch.
I did learn, by the way. Just telling you, I learned. So
Good.
thank you.
I learned that
You learned how to steer away from the flat earthers a little bit more. No, I'm just kidding.
I learned that you won't accept any evidence.
No, I do accept evidence, but the
No, you said-
wishy-washy stuff
you
with
said-
this curvature
said-
doesn't work.
You said nothing. Nothing will
Well,
convince
nothing
you.
could now at this point. And I'm being honest, nothing could at this point. There is no, okay, the evidence that we could come up with on the earth, like some kind of physical proof that's tangible and we think we're measuring it right. My understanding now is if we think we're right, we're probably wrong. Because I think there's a lot of evil in this world. We have to be careful. That's all. So I do thank you. I appreciate it though. And thank you everyone in the chat for making fun of me. It's great. I love it. I have
Thanks,
no problem
Joe.
with it.
I do enjoy talking to you. So let's.
Thank you. We'll do it again sometime.
Yeah.
We'll talk about that curvy thing you got on that picture. Yeah.
All right, everybody. We'll see you next time. Thanks. Bye.